Good morning to all. Welcome to the second day of the Advanced Drug Design in Medicinal Chemistry Workshop 2023. So we are beginning with the first session for the day. We are lucky to have Professor Raghava with us. He's a well-renowned expert in the computational biology and related fields. He works at IIIT Delhi. He has received numerous awards, to name a few. Shanti Swarup Bhatnagar Award in Biological Sciences, National Bioscience Award for Career Development, and J.C. Bose National Fellowship 2010. And he's also the Fellow of Indian Academy of Sciences. His expertise in bioinformatics applications on protein modeling, genomics, informatics solutions, integrative approaches, and applications of bioinformatics in system biologies. Today, he will enlighten us about cloud computing and what are the recent advances and challenges in this field. And certainly, I believe the audience will enjoy the talk and will have a lot to learn from him. Sir, please. Chair.
कॉलिंग माइक हो रहा है क्या? स्लाइड मूव करने के लिए छोटी क्लास है. पता नहीं वो ऑप्शन I can start. Okay. Hi, good morning. So today I'm going to talk about the advancement in the field. So sometime I give the lecture to learn new thing. It's not for you, it's for my own learning. Because the problem with the scientist, we do work in a particular area and we are perfect in our own area, but we don't know what is happening inside, means our surroundings. And I feel, at least I feel bored in working in an area for a long time. So as you can see, the pharma is not my area at all actually. From last 10, 12 years, I'm working in this area also. Otherwise, I have the different fields actually. So at IIIT, one of the duty I have actually to teach the students actually. So I teach the two courses. One is called machine learning for biomedical applications, and another is big data mining in healthcare. So this slide, whatever I'm talking, is a part of the one of my course, big data mining in healthcare. So it's just starting. Because the problem, you can talk big things, but you have to understand the fundamental things. So sometimes we know this software, we know this all sort of thing, but we don't know what the fundamentals are there. So let's try to understand from the simplicity point of view. So what are the challenge in the computers? Challenge in the computers. Initially, we had the very small computers, not powerful computers. Then you have to scale up the computers. When you have to scale up the computers, then there is a number of challenges. Either you are talking in the term of the computing, or you are talking in the term of the storage or managing the data. So how you will cope up in this situation? I will talk about them actually. And most of the things I believe in science or in the journal, it's common sense. Sometimes it's a great job. It's not a great job. It's a simplicity one actually. Let's say all these terms, I hope you know some of them already. Desktop, long time back we are using. The concept is basically personal computers. In 1980s or 80s or 90s, computer becomes so cheap that even you can afford your own computers. That's the personal computers. Earlier we cannot think about it. Only we have the mainframe computers, big computers in organizations. Workstations is just in between the mainframe computers and the personal computer, it will be more powerful. That's the definition. Servers, when you have to connect the number of devices, number of terminals, then we say. Mainframe computers, earlier, most of the institutes have the mainframe computers. Nowadays, we call the supercomputers. Parallel computing, when you have the job, you want to run in parallel, want to run on the multiple CPU, central processing unit. So you want to run that. That is called parallel computing. Clustering, because you want to do, most of you know HPC actually, high performance computing. That's nothing, it's basically clustering, where instead of one node, you have the multiple node, you have connected them so that your job is executed actually. That's an concept. Nowadays, the new concept is coming up, GPU actually. Particularly deep learning become popular due to the GPU actually. Graphics processing unit. Earlier we are using for the graphics. Nowadays this same processor have been used for computing. So it decreased the cost drastically. And the CUDA concept have come. Grid computing, when number of computers are connected via internet and then we can work in. And recent one is more towards the cloud computing. Even a lot of institutes are talking about it. Why I said to maintain the computers at my institute, because maintaining a computer, you need a big room, you need all the facility, infrastructure, even you need the experts who can maintain it. It's nearly impossible for the small organizations. So nowadays, you know, you have the cloud computing through the Amazon, through the Google's, number of options are there. They are much more cheaper. Unfortunately, still, government have a lot of tussle with it actually, particularly government of India, because they say that if I'm giving you money, you have to show me something actually. What you will show in the cloud computing actually. That's the problem. So that's the problem in the DBT, DST and all the granting agencies. When you say I need the money for the cloud computing, they say, is it the physical available? I have to, auditor will say, I have to verify it, where it is actually. So we have to change our thinking. But today the aim here is just to give you some technical idea. So mainframe computer is very simple. You have one CPU, then you have the different devices, you have a number of terminals, you can connect them and then you can work it. Okay. Then the parallel computing, you have the multiple CPUs and you want to work on the multiple. So this is the concept of HPC. HPC, you have the different nodes. And then these nodes are near to each other and connected with the, let's say, fiber optics or very fast connection actually, so that you can execute your job on the different nodes actually. Now, I want to come on the old technology called GPU actually. Nowadays, GPU is becoming very popular actually. You have to understand when you want to buy some equipment. So it's important. If you ask from me, I'm there in the field from long time actually. It's nothing, it's a simply coprocessors. Earlier, the CPU are based on the microprocessors. And at that time, long time back, microprocessors are not powerful enough. Even they cannot execute the floating points. You know the floating points? Means, let's say you have the integer number, you have the real numbers. In real numbers, you have the decimals and so on. So that we call the floating points. How many points you can go? They cannot even compute that. So they have the coprocessors. They are specifically designed to handle the floating points actually. So this concept, You have the microprocessor and there is one coprocessor that's called normally floating point unit that do the all floating. The memory there. Then later on, particularly when you talk about the motor modeling or graphics, particularly silicon graphics actually, they bring the very powerful concept where you can rotate the structures in the 3D, you can workstations actually. So you need the powerful processors actually. It's not practically possible to use your processor main CPU for that purpose. So they use the graphics card. Graphics card itself has a processor which help to rotate the image in the real life basically. Or you play with the graphics. Okay, graphics card. So people thought why we should not use it, the graphics card, graphics processing unit. Why we should not use it as a CPU actually? Because that's much cheaper than the main CPU cost. Then you will ask me the question, what is the disadvantage or why we are making the CPU when GPU is so cheap? I will tell you the problem. It's a question is basically, what is the level of precision you want? What is the level of precision you want? I mean to see the precision. Let's say if you have some number, after decimal, how many points you want to go? You want to, let's say, go into more and more points, floating points, then you need more and more computing power actually. You need the powerful processors actually. But sometimes the computation doesn't require that actually. Okay. Even a few decimal points is sufficient actually. So you should to be very careful when you are buying the CPU machine and GPU machine actually. GPU is the best actually when you need the cheap computing power, but you are not too much bothered about the high precision actually. If you need the high precision, you need the CPU. You have to understand that part. Free में कुछ नहीं मिलता है दुनिया. You have to pay the cost. So just reducing the precision, it becomes so cheap actually. So then Xeon come with the processors. That's this company. So that's some property of GPU. There is further development there actually. General purpose computing graphics processing unit. And neural network is there from over the years. Even in my time actually, when I did my master's, I studied neural network. It's not a big new thing actually, nothing new. But what new has come in last few years, that's called deep learning. Why deep learning? Because earlier, this is a typical neural network. This is your input unit. This is your output unit. Then you have the different hidden layers. You increase the hidden layers, network become more and more complex. If it is simply, let's say, input layer and output layer, that's it called perceptron. That's the easiest network. Okay, anybody can do. But that's not powerful. When you have the one network, one layer only, then this is called neural network. When you have the more than one hidden layers, then we call the deep neural network. Here, you need the powerful computers because you have to compute these weights, input to hidden to, so you need to compute a lot of weights actually, parameters. So here, you need to compute a lot of weights. That's why you need the computing power. Due to the cheaper computing power, due to GPU and other scheme, it is practically possible nowadays actually. So now the NVIDIA and other companies, they have come with the concept that would compute unified device architecture. So look like a simple device, but it includes the concept of GPU basically. So where you have the GPU computing applications, and so nowadays it's very popular. Most of us, we are buying the GPU card in our server, so that it provides the cheaper computing power. So grid computing, though it worked for some time when the internet was just started, where you join that grid computing and then they will use your computing is freely available. But the problem is there, it's not reliable and fast enough because sometimes the network is not reliable actually. So not too many people are using nowadays. Cloud computing is becoming popular day by day because maintaining computers is a big deal. Because let's say you are the student or you are a researcher, you are maintaining your group. You are not computer expert. How you maintain it? That's a problem. So rather than you maintain, somebody is maintaining. Whatever the computing you need it, you do your job because you are interested to solve your problem. Let's say you are the pharma person, you want to run the QSN models. Why you should to maintain the elephant, the whole computer actually? You just load on that this computing power. You take cloud computing, buy it, and run your QSN model there actually. So cloud computing is becoming popular. Private cloud computing, when a company have their own private network and they allow only that network, we call private. Public, like number of like Amazon or Google and all these things, they have the providing you the power, you pay to them. Even if you are a student, you want to try the Google cloud computing, it's freely available for the student for some time, or you want the limited power, or then it's freely available. Then Amazon is also there. Some of them is a hybrid in the model. Okay, so wide range of application can be launched over. The question is basically, you will have the question in your mind, how I will run on the cloud computing? Because there should be some way. All right. So there is a one concept, very powerful concept is coming up. That is a basically VMware, where we are called virtual operating systems. So in VMware, we have the host operating system. This is, let's say, it's there on the Google, hardware is there, everything is there. So you have the host operating system, let's say it's a Linux. Then you want to run your own operating system. Because one hardware will take only one operating system. So how you will manage many operating systems on a single machine? So there is a concept of VMware, where you can have the guest operating system. Maybe this is your application, you load it here, and you have the everything access to this. This is a virtual CPU. They don't have the actual CPU, but they are using the CPU power from here. So these are called the virtual system. So in the same machine, you may have a multiple operating system. It may be Unix, it may be Windows, or different operating systems, depending on your requirements. So we have to understand the concept that on a single machine or single operating system, we can put the different operating systems. These are called virtual machines. Virtual machine, we are called VMs basically. So in this virtual machine, once they allocate it to you, then it belongs to you. You are the root password, you have the access to the root. You can give the username, you can load the libraries, you can do whatever you want. You will feel that this is my own computer. Okay. So that's a concept. So virtual machines, they are very popular. So I'm again replying because nowadays, even in our own institute, I will tell you the real problems. In our department, we got something like 50 lakh rupees. We brought some computers. We have the 11 faculties in our department. Every faculty have their own need. Some need Unix, some use Windows, some other operating systems. As well as every faculty wants different type of library, Python libraries or other libraries, and it's nearly impossible to give the different powers to the different faculty. So what we have done, we have loaded the 11 VMs, virtual machines, and for each individual, we have given full access to the one faculty. It's up to the faculty what operating system they want to run, how many users are there in the group, what softwares they want to install, what libraries they want to install, they're free. So the concept here actually, we have buy the hardware and then we have buy the operating, not operating system, this is a hypervisor actually. This is called hypervisor. Over the hypervisor, you can load the different VMs basically. So now everybody is happy in the department, they are using the facilities. And nobody can disturb the others because the memories, CPU computing power have been allocated. And the advantage is there, if you are not using, the other can also use it. That's not big deal. So you are not wasting your power. Right? So this is the important why I am talking to you. Because you are young, right? You have to go into future. And in future, you have to manage the resources. Because if you talk about the computational chemistry, computational biology, or any theoretical science actually, managing computers is a big thing. All right. There is a new concept. The problem I will tell you with the VM, virtual machines, is that they do the dedication of work. So they are very powerful, but they do the dedication type of work. So let's say if I have given to the 11 faculties, so there will be 11 operating systems are running. So there will be overload. So instead of one operating system, you are running the 11 operating systems. Though everybody is independent, everybody is doing whatever they want to do it. But problem is there is a 11 time resources wastage, particularly operating system level. So there is a lighter part that's called Docker. Docker is a software which is similar to VMs, but the difference is here actually, it's using the operating system of the base. So even let's say you have VM machine. In VM machine itself, you want to give the Docker to your students actually. Let's say in your group, you have the 10 students and you want each student should be independent, they should work in their own area. Then you can give the Docker to each student. So Docker is light, it's not for heavy work, but Docker are using minimum energy or minimum computing power because they are using base computers. Okay. So that's a concept of Docker, depending on your need, whether you should use the VM or you have to use the Docker. But both VM and Dockers are supported by all cloud computing service providers. Either it's Amazon or it's Google or whoever is there. So if you have the knowledge of, let's say, Docker, you make your Docker, put on the Google Cloud Computing, and then you are working independently, you are not bothering about it. Only you have to pay the cost actually. But if inside your own institute, if you have the computers, you can load the VM and Docker. So I'm not going into the detail. I have already loaded my slides. I hope you got the folder or you got the, I have shared with them actually. But that's the only thing what I feel different than most of the researchers in country. What I feel I have done differently. From the day first, when I started my publish my first paper, every document, every presentation, every code is freely available to the public. That's the only difference I made over the time. Because I have seen over the years that we are too possessive. We will die, but we will not share our knowledge with anybody. Actually. That's our habitat. We feel that we will be forever. हम अमर रहेंगे, कभी नहीं मरने वाले. कभी किसी को शेयर नहीं करना, पड़ोसी को नहीं करना. That's what I don't like. So science, scientist तो बन गए, science वाली feeling नहीं. Scientist means you are for society, you are contributing something, not only for making your own career. So you can see, go to my website, you will find a number of Python code, Perl code, everything, whatever we have developed, we have provided free to the public. Because we don't find that competition will be there. All right. So all slides, everything is there. You can use that actually. So again, I am describing the concept of Docker and VM machines. So in case of the VM machine, let's say you have the host operating system, means the operating system which is on the hardware. Then you have the hypervisor, some software which provides the interface between two. Then you have the virtual machine. So you have the guest operating systems of that virtual machine. This is virtual machine 1, this is virtual machine 2. So both have their own operating systems. So they are not using this operating system. They are using independently. So that's the concept of VM. In case of the Docker, you have the host operating system, like other. You have the Docker engine. That's again software which provides the interface. But this is Docker 1, this is Docker 2. But here, no guest operating system. They are using the same commands from here. So they are not running their own operating system. So this Docker concept is good when you have the small applications. Let's say you want to run a database. You want to launch your database or small application, then Docker is it. But if you want to do the heavy computing jobs, then VM is the best. Depending on the need. And both technology is required when you talk about the cloud computing, because that's the way that Amazon, Google, and other companies are providing service to the community. They have the let's say in case of this, they have the hypervisor host operating system. So when you ask them, you want to run a VM, they say load your VM, and that VM will load it here. Once it is loaded, then it has a complete access to you. You can do whatever you want to do. Okay. So it's like a sort of container. In the container, you do whatever you want. So this is a complete container. That the idea is basically, let's say you are doing, let's say, for example, I will tell you a very good example. I worked at Intech Chandigarh, Institute of Microbial Technology Chandigarh, for 30 years. Okay, at least 15 years I developed the software. When I moved from Intech Chandigarh to IIIT, the problem was I have the more than 200 web services with me. Okay, and everything is working perfectly all right. So how I will shift them? So what I did, I put in the VM virtual machines, and then I copy it on a hard disk, bring the hard disk. Okay, and at IIIT, I launched the VM and I started. Everything is working fine, except some links and other things. That's a small thing. So you see, it was not practically possible to develop, to configure again all these services. But due to the help of virtual machines, it is easy. I will advise you to the young faculty or students, please make your own Dockers or VMs from now, because you are doing PhD now, for example. After that, you have to move to somewhere in the US or anywhere in the world. What will happen to your softwares? Who will maintain them? And whatever library you have installed it, you have to reinstall it again. So it's a big headache actually. So it's better from beginning, you have planned for the long term actually. So you have your own container, keep everything, put operating system, run here. When you want to go to some other place, you just take it and put it. There's some few more advice I am giving to my PhD student also. I'm giving to you also. Please make your own websites. Nowadays it is freely available, either WordPress or Google site. Number of sites are there. Because whether you like it or not like it, advertisement is the important job. Even if you do a good, excellent job, and if you are not advertising it, nobody will use it. That's where the difference is there between the commercials and freewares. Most of the freewares, they are not so popular. Why? Because nobody is promoting them. Because scientists are too egoistic. Let's say, for example, I develop some software or website. If user wants some more customization, I say, go to hell, I don't care. I'm researcher, I'm busy, blah, blah. Okay. But if you talk to the commercial say, no problem. You give me money, sir. I will do whatever you want. That's the difference. That's why the commercials are more popular than the events. So it's important for you that make your websites, everything. So even let's say you are doing B Pharma and Pharma here, you go any other place. So at least your website is there. Give, instead of giving the card to anybody, give the URL. Now even you can have your own domain name. You may have your own name, .net, .org, blah, blah. It's very cheap actually. That's nothing is there. But only thing you have to think of. Anyway, so the idea with the Docker and even VM, the concept is build it, do whatever the work you are doing. When you are going somewhere, you lock it, copy it on the hard disk, and deploy on other machine. So let's say today, because every machine, computing machine, have the half-life. Most of the machine, they work for 5 years. Even after 5 years, I never go for the maintenance. Why? Because in 5 years, computers have become so cheap. The money you are spending on the maintenance, you can buy the new machine of the same specifications. It's changing world. Okay. So why waste the money on the maintenance games? So when you buy any machine, buy for with the AMC for 5 years. After that, if it works, it's fine. If it doesn't work, go to hell. Simply buy the new machine. That's the concept. And main problem is starting the software. So put into a Docker or VM so that you just copy it, load on another machine. You are not bothered or what type of hardware. So it becomes a hardware independent. So the advantage here is you work in the container, you do the modifications. After modification, you want to save it, you just save it. So whatever the work you are doing, you can, it will be automatically saved. And when you want to move it, the latest version will be copied. So this is a site from where you have a lot of software. Another part is basically whatever the work you have done, how you will distribute it to the public. Please remember one thing. If you are experimental science, that's a different situation. But if you are from computers, for what anybody should recognize you. Okay. So your softwares, your websites, or your any application. Let's say I will say the change of the time. Initially, when first software have developed by our group, we distributed through the floppy. Not too many people know the floppy actually. Floppy is a small device, 3.5 MB storage there actually. So we, okay, later on this technology obsolete. Then CD come into the picture, or DVD, CD or DVD, they come into the picture, that also. Nowadays, it's mainly web-based services. Why? Because nobody want to install the softwares in their machine. User is becoming lazy day by day. Yeah, that's a fact of the life. They need a cooked matter. They don't want you give the instructions, read the instructions, blah, blah, blah. They are not. What they want, click, click, click. That's why mobile become popular actually. Even the people who are not educated, they are using the mobile day to day because it's so easy to use. So if you want to become, because that's the lecture I give to my students, because most of my students there, they are computer science students. I say, if you want to become the good computer scientist, you have to understand the need of the person who is hardly any education, so that anybody can use it. Because it's very easy to design a software, design any product for the persons who are equal to your level actually. That's not big deal because you can give the instruction, the person will read. But reality, if you really want, public should be your user. Then you have to design in such a way so anybody who has the little knowledge about computer can still use it. And web technology is such a way, let's say, for example, web services, web servers. You just go there, you have your chemical, you type there, you type the formula, and it can calculate whether it's an inhibitor, non-inhibitor, it's toxic, non-toxic, whatever the facility is there. So easy actually. So why I used to load on some machine and do the lot of work. So web technology is very important nowadays. Mobile applications is another good example. So mobile technology has a different concept that we call stack. One is called full stack. Full stack means the person should have the complete knowledge of the web technology. It means the person should know the HTML, Python, CSS, and all sort of things, so it can launch it, it can work it. Not necessarily he's an expert in everything, but have the broad knowledge. For example, I'm doing that full stack job from the last number of years, where we develop the software, we provide the front end, we provide the back end, everything. So we provide a complete solution. So full stack means complete solutions. So here you have some operating system, databases, web servers, and then you have the client side. So client side, how it will connect to you through the browsers, maybe Google Chrome or maybe Safari or whatever the browsers are there. You will connect them and the web service. So you have to learn that how to load the different web services. How many of you are from B Farm? Not too many. Okay.
All of them.
Huh?
Most of them.
Most of them. Why I'm asking this is my experience over the time. Most of the people who are young, they can learn anything because they don't have any inhibition. As you grow, inhibition increase. And after a certain level, you never take the risk to change yourself. You do whatever you have done. Let's say, for example, because I have seen myself actually. Most of my BTech students who come to me as a project and all sort of things, you ask them anything actually, they will do it without questioning. They will learn the new thing, they will read it, they will do it. If you ask MTech, it's okay. PhD, they have no option, they have to do it, they have to listen the book. मजबूरी का नाम महात्मा गांधी है, क्योंकि क्या होता है मेरा स्टूडेंट मुझसे लड़के क्या करेगा, ठीक है, सीख जाते हैं. PDF को सिखाना मुझे बहुत डिफिकल्ट है. Number of students join me in my group as a PDF who learn from the other places. They are doing everything, research work, everything, but not changing themselves, programmers and all sort of things. I'm not saying it's true for all, but it's true widely actually. जैसे जैसे बड़े होते जाते हो ना, इतने पकते जाते हो, उसके बाद अपने आप को चेंज रिजिड होते जाते हो, रिजिडिटी चेंज नहीं होने देती. So you can easily change. I want to give the message, nothing is difficult. Because sometimes you are not from the computer science, you feel that programming is a big deal. Nothing is there. I'm giving you instruction, you do this job, you do this job. And then sometimes I give you the steps, you do first this, then do this. This is the instructions. And same instructions is a programming language, nothing more than that actually. Let's say we talk in English or any language. Here we have the Python, Perl, and different programming language. There's a set of instructions. We are giving the instruction to the computer. So we have the set of protocols. So if you have no knowledge, don't worry, you can learn it. That's not a problem. Only thing, you have to remove your inhibition. That's all. Okay, so this is a full stack concept when you have the everything. Let's say, for example, you want to become a web server developer, like we are. Don't worry too much. There is one software called LAMP. Linux, Apache, MySQL, PHP. LAMP. The name of the software LAMP. Okay. You just download it on your machine, install it, everything done. I am giving you the guarantee within 2 or 3 days, you will be fine with it. Okay. Only thing you have to have the courage. That's all. If you are on the Windows, then there is a WAMP, W-A-M-P, Windows. Okay. Windows, Apache, MySQL, PHP. That's the best actually. If you want to use on any machine, that JAMP software is there, JAMP. So nothing is there. Why I am telling this software? This is very easy, where it allows you to create the websites, create the databases, all sort of services. You can easily do it. And another advice I have to my youngers actually. In today's time, Python is doing very well actually. Python program. At least learn one program. If you learn one programming language, learning the other programming language is not a problem. And Python at this moment, at this time, is the best. Why? Because too many libraries are there. You want to implement the deep learning, you want to implement the machine learning technique, any machine learning technique. Scikit library is there. Just change the command, use it. So the message, ultimate message from my side is, it's not difficult actually. Only it's fear in your mind that you cannot do it. Remove that fear actually, and you can do it. All right. So this length system worked very well. And I don't know how many people are interested in the mobile application development. That's a concept for developing the mobile applications actually. Okay. There, if you want to really develop, then I will advise you Java. Python is not good for the mobile application development. Still, there is a lot of challenge out there. So Java is the basically native language for that. So these are the front-end technologies. When you are developing your web page, HTML is the easiest way. Hypertext markup language, because we cannot use the Microsoft Word, documents, or display or Acrobat Reader PDF, because they have the escape characters. So internet, we cannot transfer the escape characters. So we have the HTML. That's a hypertext markup language. It means there is a text and we have some markup. Markup is still made of text actually. Let's say if you want to make the bold, so then you have the greater and lesser sign, and then you say B. It becomes the bold sort of thing. So HTML is easiest one. If you want the style, then CSS is there. You want some client side computation, JavaScript is there. Web frameworks. So number of, because time will not permit me today all these things. So these are the basically full stack technology. Backend normally we use Ruby, Python, PHP, Java, any or computational work. Okay. For database management, though there are a number of database management are there, but MySQL is very popular, which is freely available. You can use it. Okay. If you are handling with the large data or big data, then SQL technology doesn't work. Structured query language technology does not work. There is a new concept called NoSQL. Doesn't mean no SQL. It means not only SQL. It means not only SQL. Please try to understand that. NoSQL technology. Okay. And NoSQL technology like MongoDB is there, TuffDB is there, Hadoop is there. So nowadays, when I teach my students, that these are the technology for future when you want to store the big data. Hadoop with this technology. Then nothing difficult. If you go to the Dockers, number of Dockers are there, which are preloaded with these Hadoop and all sort of. So it's not difficult. Then there are servers to launch the websites. I prefer to use the Apache, but there is a beyond that NGIX. I never use it, but it's your choice actually. So these are the different popular stacks. How you run them actually. Though we are comfortable with the LAN, top one, but beyond LAN, there are a number of systems are there. Let's say if you are Python expert, why you will go to the LAN actually? you can go to the, let's say, this Django stack, JavaScript, Python, and concept basically. My slides are available, so you can read them. That's not problem. So in HTML, that's a EGST. All your websites is through the this protocol HTML, where you have the browser this side, you have the web page, and through the internet you are connected. Though you all understand all the things, but this is a concept basically. Sometimes you will see here HTTP. Sometimes you will see HTTPS. So S is nothing. It's a basically secure one, because HTTP is not a secure protocol, hypertext transfer protocol. Okay, then the HTTP, as well as you have the FTP, FTPS. Okay, then this is the domain name. Then by default it takes the port 80 if you don't define it. Even if you don't say anything, it will take port 80. And by default it takes index.html actually. And this whole concept is called URL basically. Okay. So here it will take by default port 80 and index.html. These are the, because in the Unix, when you talk to the Unix, then there is every service is through the port number. There is a concept of port number. So every service is provided through the port number. Let's say web service is through the port 80. Let's say you are doing FTP through the 20 port number 21. So there are different ports. So service is provided through the ports. These are some default ports you can remember. Okay. So HTML is for building the websites, CSS for making the styles, JavaScript for functional work. So because I'm already more than allocated time, so I'm going fast actually. So I have to finish within the time. So this is a typical HTML code. We call these are the tags. So here it's a HTML starting header. This is a title. So it will look like title here. We say this is the body, the colors, and this is typical one web page. So everything is through the tag. We call this is a tag actually. If you want the bold, say write B here, it will become bold. So I have to jump because that is not practically possible to cover everything. But these are the codes for PHP, how they look like them. Why PHP is preferred? We have to understand the facts. Why we are not using Python here? Because PHP have the advantage, it can be integrated in HTML. You are writing the HTML code, everything, and in between you need some computers. You can integrate the PHP codes. That's the advantage. So, so you have the HTML code, and within the HTML code, you can do the PHP. This is CSS basically. Anyway, you have the JavaScript. So this is the advantage. You are writing the HTML code, and all of a sudden you feel you need to do some repetitions, you need to do some computations. So PHP is this programming language. You say question mark PHP, and then you write the code, you finish the code. So within the HTML code, you can do the computations. All right. You can submit the form, you can do the lot of work. Another thing you have to learn about the CGA. Because let's say you go to our website, you'll find that there is one form is there where you can fill the form and also then you say submit. And what will happen? Then it will go to the CGI, Common Gateway Interface. Then our Perl script, Python script, whatever depend, they will execute it and they will send result to you. That's called Common Gateway Interface. So you have to understand a number of programming languages support this CGI. Okay, so of course Apache is one of the best servers. You can use it, and this is the configurations concept is there actually. So, because today I was supposed to talk about the advancement in drug discovery, that's not practically possible. So I only talk about some technology only. But I will advise you to read this review if you have some time. Actually, it is available. And this website, most of the tools, because what I'm doing over the years in our group, what we are doing, we are just collecting and compiling all the freewares time to time and putting it to the public. So they are getting awareness from single source, they can get that. So here you get the all sourcing, and the title is Computational Resources in Healthcare. It's not drug discovery, bioinformatics, and chemistry. Because in public, there is a lot of confusion is going on. Some people are saying bioinformatics, some say chemoinformatics, pharmacoinformatics, clinical informatics, immunoinformatics, anything in informatics. But most of the cases, what is a purpose? It doesn't matter where you are working. What is a purpose? Most of us, we are working in the healthcare. Means we are trying to improve the health. Okay. So what we did actually, we combine all these fields, all the resources. We put the healthcare, and then we divide it into drug discovery, whether peptide protein based, small molecule based, toxicity and side effects, vaccine development, adaptive or innate immunity, disease biomarkers, like the cancer disease biomarkers and no biomarkers, and healthcare nowadays new technology, IoT, where you have the smartwatch and other things, and they tell you that what is your step you have run, what is your heart situation, everything actually. So these are called IoTs, Internet of the Things. Okay, these are the. So we combine it, and then for each topic, we have put this sort of tables. If this is for small chemical based discoveries, you have the name of server, a brief description, and the URL, right? Another review which we write long time back is for open source software. Why we are writing the review time to time, so that you get the awareness. There are a number of free softwares are already available. They are as good as any commercial softwares. Only thing you are not aware with them. You are not reading about them. Okay, that's why I'm giving. This is another review on the protein and small molecule interactions. This is for the generation. So some reviews I have given to you. And this is a new topic we have started in our group that is called fast-based therapy. Because the fast-based therapy was there even before the antibiotics. But the antibiotics become so cheap, so easy to avail. So the fast therapy go into back burner. But nowadays, due to the drug resistance, now people are thinking about the alternate strategy. One of the strategy is fast-based therapy. Fast means the virus which kills the bacteria, which kill the pathogen. That is called fast basically. So now we are. So this is the review we write actually. That what are the computer resources in this area actually, because this is a coming up field and FDA is now giving the approvals in this area. Because sometimes it's important for you, a particular young guy, to explore the new areas rather than working over the years. Because what is the problem? Your boss is working, you are working in the same area, you want to continue the same area, how your boss will allow you to survive? उसके नए स्टूडेंट आएंगे, उसका इतना एक्सपीरियंस हो, तुम्हें सर्वाइव नहीं करने देगा, छोड़ दो एरिया इमीडिएट नए एरिया पकड़ो. ये एक रीजन रहा है कि यूएस से आने के बाद हमारे काफी लोग फेल हुए इंडिया में. मैंने इंटेक में देखा, we got the people from the US and other places, they did the PDF, they did very well, good job. When they come here, they are completely failure. Why? Because they don't want to work, explore any new area. They want to work in the same area what they are doing in the US. And US, they have all facilities, powerful, they are not able to survive. They survive here, they just work. Doesn't matter much. So it's important, always try to explore the new area rather than you follow the people's, try that you lead the area. Thank you very much. Sorry, I am a little bit late.
Thank you very much, sir, for your kind advice and a wonderful lecture, which is very much required for this audience who are just beginning to explore computers and their applications. And if we can combine those understanding of medicinal chemistry with the latest technology, then we can certainly do wonders. So with this, I would like to welcome Professor request Professor Kharkar to felicitate Professor Raghavan. So please, team. So our next speaker is none other than Professor Kunal Roy. He is a world-renowned expert in the field of QSAR and read across. Currently, he is a professor in the Department of Pharmaceutical Technology, Jadavpur University, Kolkata, and he also has numerous awards to his credit. Oh yes. Hello. Online. Yeah. So welcome back after a short tea break. So we have Professor Kunal Roy with us. As I mentioned earlier, he is professor and ex-head of the department in Jadavpur University, and he is a leading expert in the field of QSAR and read across technology. And he has numerous awards and top rankings to his credit. So without keeping him away from you, I would like to invite him to please start his lecture. Thank you, sir.
Okay, I have 40 minutes.
Yes, yes.
Thank you very much for the nice introduction. Good morning, everyone. My today's lecture is on the QSR, the QSR approach as a novel ML-based tool for activity, property, toxicity endpoints. So actually, usually I give lecture on QSR, so I wanted to start with QSR, but it's QSR, which is somewhat related to QSR, but not exactly. So I'll start with QSR. As you know, that QSR is the acronym of quantitative structure activity relationship, which is a statistical modeling process for correlating a response endpoint with structural or physiochemical information in the form of descriptors. And we collect data from various sources, which can be online databases or from literature, handbook, scientific articles. And there will be biological and chemical curation of the data. And we take the input data containing the activity, property, or toxicity points after appropriate treatment. And then we go for descriptor calculation. Now, these descriptors means the chemical information quantity in the form of mathematical quantities. They quantify the chemical information. And the descriptors can be computed using various tools like pattern descriptor, traveling, alpha test, and so on. And then we go for dataset division. Now, this is important because we have to validate our model. So For development of our model, we use training set, and for validation, we use test set. Test set molecules are unsafe to the model. We do not use the test set compounds for model development phase. We use it developed. Pin set is used for model development, and the division of the data set into training and test can be done using different methods, which can be random division or maybe some similarity-based approach like stone activity-based, Euclidean distance, k-meters, etc. And then using the training set data only, we go for feature selection using methods like genetic algorithm, stepwise selection, and so on. Then we apply appropriate learning algorithm, which may be supervised or unsupervised. In case of supervised method, there may be regression-based model or classification-based model. And in case of unsupervised, we do not use the dependent variable. It can be clustering or dimension reduction. And finally, the developed model is validated appropriately, and the applicability domain of the model is checked, and it is subject to mechanistic interpretation, and it can be used for designing new models. This is the basic theory of QACR. But today, I'm not covering QACR. But before we proceed, there are various applications of QACR in pharmaceutical science, material science, food science, agricultural science, nanoscience, predictive toxicology, etc. for prediction purposes. We can use QACR for data gap filling, for data points for which do not have the experimental values available, but we can apply a properly validated QACR model for generating or computing the endpoint data. Now there is another concept which is also similarity based, that is read across. This is originally unsupervised method of prediction, and it has been used especially in case of toxicity data gap filling, where a similarity can be considered not only based on structures but also based on different properties, toxicities, metabolic behavior, etc. So based on various sources of information about structure, features, property, toxicity behavior, metabolic behavior, etc., we can define similarity, and we can predict the endpoint values of query compounds based on some source compound. So we have to identify the source compound, appropriate source compound for a particular query compound, and we can confidently predict a particular endpoint based on the similarity-based approach. Although it is an unsupervised approach, but we can incorporate some degree of supervised modeling approach here. Now, recently we proposed a quantitative read across workflow where we start with a data set and we divide it like QSR, you say training and test. Actually, these are called source compounds. Training compounds are called source compounds, and test compounds are query compounds. And these training set compounds are also divided into sub-training and sub-test set for hyperparameter optimization to select the appropriate hyperparameters to define similarity. And here we have used three approaches: Euclidean distance-based approach, Gaussian kernel-based approach, and Laplacian kernel-based approach. And we calculate the endpoint value based on weighted average predictions. And we can calculate the endpoint values of the query compounds based on weighted average prediction from the appropriate source compounds. And then we can apply the usual validation matrix as we use in QACR. So this is the workflow for quantitative read across. With more example for better clarity, say for example, if our query compound is bromobenzene and if we have several source compounds like say toluene, chlorobenzene, hydroxyphenol, etc. So we will compare the similarity of the query compound to the source compound based on different features, which will be structural features or some other property. And we will identify the appropriate source compounds, and based on the similarity between the query compounds and source compound, we'll give appropriate weightage, and finally, based on this appropriate similarity based on Euclidean or Gaussian kernel based or Laplacian kernel based, we'll calculate the weighted average prediction in the quantitative readouts. Next comes the approach of NASR, which is read-across structure-activity relationship, which is a new concept where the read-across and QSR can be merged together. So the original concept of unsupervised prediction with the supervised learning process can be merged together in NASR. And this concept was originally applied by Lutchfield et al. In 2018. But they applied in classification-based predictions. They used two metrics, maximum positive and maximum negative. That is the maximum similarity value towards positive compounds and towards negative compounds. Only these two metrics they used in classification-based modeling. But we have included these for quantitative prediction, and we have proposed a series of similarity and error-based metrics for this. And like the previous quantitative read-across workflow, here also we use training compounds for read-across based predictions. So we divide them to sub-training and sub-test set. This can be done several times, 5 or 10 times or more number of times if desired. And we choose the appropriate similarity measure. We choose the appropriate hyperparameters for descriptor calculation. So based on the read-across based hypothesis, we calculate Russell descriptors. So what are these Russell descriptors? I'll come to this in the next slide. And then we do data fusion. The data fusion between the structural and physicochemical descriptors, the original ones with the Russell descriptors. So we get a final pool of descriptors selected by cross validation. And then we develop the model and we apply on the tested compounds. Now, these are the various measures, dispersion and similarity-based measures. The ST activity, CV activity, and similarity-based measures include average similarity, ST similarity, maximum positive, maximum negative, absolute difference between maximum positive and maximum negative. And a concordance measure G that was proposed by Wu et al. In a different context, but we have used here as a concordance measure. Originally, it was used for interspecies, but here we have used to define similarity. And in more detail, the weighted average activity, this is just weighted average mean. The SD activity, that is the weighted standard deviation of the response values of the original source compound. This is the coefficient of variation. This is ED-based similarity function using the usual Euclidean distance function. This is the Gaussian kernel-based similarity using L2 norm. This is Laplacian kernel-based similarity using L1 norm. This is the average similarity. That is the average of similarity towards the closed source compounds for a particular query compound. This is standard deviation of those average. This is maximum positive, maximum negative, then difference between maximum positive and maximum negative. And the concordance measure, which uses the positive fraction among the closed source compounds. What is the fraction of compounds belonging to the class positive? And this is a modification of G, the previous concordance measure, where we have modified the formula here. We use -1 to the power n when maximum positive is more than maximum negative, and the opposite, in case of opposite, it is 2. It is just to give a dimensionality to the value of GM. That is because the value of G may be same for positive fraction 0.6 and also negative fraction 0.6. So it can attain the same value when the percentage of positive compound, positive source compound 0.6 and negative source compound 0.6. Similarly, it may be say 0.4 when the percentage of positive source compounds 80% and negative source compounds also 80%, same value. So to remove this redundancy, we have defined GM, the novel concordance. And also we have defined another function, that is RA score or RA function, which is actually a latent variable like measure, which is derived from multiple descriptors. And we use this as additional descriptor for our Russell model. And there may be several scenarios here where the maximum positive is more than maximum negative. So in such cases, when the positive fraction is 1, GM value will be 1. And here you can see positive fraction is 0, the GM is -1. So GM will take values in the positive scale when the positive fraction is higher than 0.5, and GM value will be in the negative side when positive fraction is lower than 0.5. And this figure explains the RA function, which is based on similarity to the similarity of the query compound, the source compound. So we need additional descriptor along with RS score just for precision of the predicted values, because for a number of compounds the RS score may be same, because for a number of compounds the closed source compounds may be same. So for precise prediction we need additional predictor, which may be the original source physiochemical and structural descriptors. So we start with our chemical data set, and we have the endpoint values, quantitative endpoint values, and we have our chemical information in the form of descriptors. And from this, we apply the unsupervised similarity matrix generation. So in our case, there is some degree of supervised modeling because we use weighted average prediction. And then we apply this to select the appropriate similarity measure. And then we can apply the supervised learning process, which may be the simple model building process like multiple linear regression, or we can apply the machine learning based techniques also. And we can actually develop model for multiple endpoints, and we may be able to relate these to multiple targets or multiple molecular initiating events. So to in an approach of AOP, adverse outcome pathway. So this can be linked to AOP. But here we give some examples of raster modeling using only selective endpoints. So the case studies that I describe here are for single endpoint, not for multi-objective learning process. And we use chemical data set with quantitative response values. We compute 2D descriptors for simplicity here. And then we divide the data set into training and test. We go for feature selection to identify the important features which are important for particular endpoints. And we also develop chemical similarity-based measure and similarity-based matrix. Then we combine these two, the structural and physical descriptors and the similarity-based descriptors, and we develop our raster modeling, which can be used for prediction of tested compounds. Now, for raster descriptor calculation, as I mentioned, that we have to start with our data set. We calculate our structure and physical descriptors. Then we divide in a QSL-like approach into training and test set. But raster descriptors are calculated after division of the data set into training and test. Usually, descriptors are calculated for the whole set first, then the data set is divided into training and test. But raster descriptors are calculated after division of the data set into training and test, because raster descriptors are based on similarity-based approach. Here, the source compounds are training compounds and the test compounds are query compounds. So each of the query compounds, they are subjected to similarity to the training compounds, and based on the similarity level, the raster descriptors are calculated. And for this, we need a number of hyperparameters. For example, say gamma in case of a Gaussian canonical-based function, or sigma in case of Gaussian canonical function, gamma in case of Laplacian, number of closed compounds, and so on, which we obtain based on the cross-validation approach from the training set on. And after we fix our hyperparameters, we calculate raster descriptors for both training and test. Now the question comes, how we calculate the raster descriptors from the training set? For the training set, we calculate raster descriptors using the training set. That means for raster descriptor calculation of training set, we use training set both as the source and query compound. And we use here leave same out approach. That means for a particular query training set, we remove that particular training compound as source. And in that way, we calculate the rasa descriptors for the training set. And for the test set, it is in the usual way. And after that, we club the rasa descriptors with the structure and physiochemical features. So we use the combined pool of descriptors. We do feature selection again based on the training set. We develop the rasa descriptor, rasa model, and we go for prediction of tested compounds. And also we apply the concept of application domain. Now I will give some case study examples. The first one is modeling of androgen receptor binding affinity. We start with 208 compounds. We do structure curation using a NIPER workflow. We calculate descriptors. We do data pre-treatment. Then we go for dataset division into training and test. And we had 103 compounds in the training set and 44 compounds in the test set. We had to delete some compound based on our curation. And then we do our usual QSR modeling for feature selection. And then we do go for quantitative data loss here. And based on that, we calculate different singularity and error-based descriptors. And this is the original QSR model without using any rasa descriptor. This is the original QSR model. Using the structural and physiochemical variables, those who are conversant with QSR analysis, they can identify that is the E-state and the constitutional descriptors, the physiochemical descriptors, and so on. Now, for any QSR model, we have to check the quality of the model in terms of different metrics, like internal validation metrics. Say, this is leave one out cross validation coefficient, this is 68%. And for external validation, it is 0.58, the classical Q-square F1. Now we go for the rasa descriptor calculation from the structural and physiochemical variables, which are these ones, the selected features. And I have already shown what are the rasa descriptors like maximum positive, maximum negative, the SD activity, etc. And when we develop the individual QRASR models using our base subset selection method, we got a number of models, and also we developed models based on pooled descriptors from these individual models. I'll show the quality. Okay, before we go to the quality, if we show the importance plot, relative importance of different descriptors in a bubble in the shape of bubble plot. Here the bubble size is that corresponds to the variable importance. And you can see that in most of the cases, the most important variables are rasa descriptors. Here you can see the maximum positive and then average severity. This is the maximum negative. And here the second descriptor is rasa descriptor. Here the first two descriptors are rasa descriptor, rasa descriptor. In most of the cases, most important descriptors are rasa descriptors, not the structure or physical descriptors. Okay, this is loading plot. As you can see, this is a plot of the two LVs of the first two LVs of the PLS, and you can see the rasa descriptors are very near to the endpoint, that is log receptor binding affinity and routine receptor binding affinity. So more close a particular descriptor to the endpoint, more important it is. In most of the cases, the rasa descriptors are very close to the endpoint, showing importance for the particular endpoint. Now, if we take a comparison of quality of models, you can see these are the individual models, these are the pooled descriptor model, and also we have done the intelligent consensus models. And you can see here that for the query set, the Q square F1, if we say Q square F1, Q square F1 is maximum here. And if you see the minimum value of MAE for the query set, that is here. That is the intelligent consciousness model 3. And this is the original QSL model without any raster descriptors, using only structure and physiology. As you can see that its Q square F1 value is much lower than this one, and its MAE value is much lower but higher than the best raster model. That means here, after introduction of raster descriptors with QSL descriptors, the quality of prediction has increased. Now, one more thing I will mention, that the raster descriptors are calculated based on selected features which are used in this QSL model. So no additional chemical or physiochemical features have been included here. That means with the same level of chemical information, the external prediction quality increases after incorporation. Now, I mentioned initially that we have modified the original value of G to GM, and when you include GM instead of G, then the quality of model further increases. The initial Q square F1 value of QSL model was 0.58, but this raster model shows the external validation metric is 0.674 after introduction of GM. And if you see the variable importance plot, the GM becomes the second most important descriptor compared to G, which was here. The second case study, that is, we have used here 5 different endpoints where we have used the raster modeling approach to model 5 different endpoint data. Again, androgen receptor binding affinity, then the avian toxicity of white quail, then honeybee toxicity, another avian toxicity, mallard duck, and inhalation toxicity of volatile organic compounds. Now here we have again used androgen receptor binding affinity because we have included here one more raster descriptor, that is RA function, that was not used in the previous case. Now this is the relative importance of different descriptors. For this for data set 1, this for data set 2, this for data set 3, and so on. We can see in most of the cases, raster descriptors shows very much importance, and this importance is shown in the form of the diameter of the bubble. And you can see the raster descriptor shows the bubble size, high bubble size. That shows the importance of similarity-based descriptors. Here also, we can see that this is very much important, GM into average similarity. And here also, number 5, this shows high importance in the VIP plot. Now, if we compare the quality of models of QRASL model in comparison to corresponding QSL model, one thing should be remembered that the chemical information content of QSL and QRASL model was same. That means we have used same set of descriptors, chemical, structure, and physiochemical descriptors for QSL and QRASL. But if we see the external validation matrix, Q square F1 has always increased. It is 0.70 in comparison to 0.58. It is 0.77 in comparison to 0.65. It's 0.83 in comparison to 0.65. And MA value has decreased. It is 0.44 in comparison to 0.54. It's 0.35 in comparison to 0.46, and so on. And this may be different scenarios actually, where this is a query compounds and these are the closed source compound. And if this is the Y mean, that is the mean response of training compounds, all compounds above these points will be positive and all compounds below this will be negative. Now you can see for this particular query compound, all closed source compounds are positive and maximum positive value is very high. So maximum negative will be 0. And in this case, GM value will be towards high positive. SD activity will be low because the closed source compounds are very near to this particular compound. So SD similarity will also be low and RA function will be higher. In the second case, here this is the query compound, these are the source compound, but these are not very close like this. And all of them are positive, but not as much positive like this. So in this case, the maximum positive will be low, maximum negative will be 0. GM will be positive, but lower than this one. SD activity will be high, is disparity will be high. RA function will be positive, but not as much as this case. Now, in this scenario, this is your query compound, it's just borderline, and these are the source compounds. Some of them are positive and some of them are negative. So in this case, what happens? Maximum positive will be low value, maximum negative will also be low value. GM value will be close to 0. That means these are borderline compounds. For such compounds, the decision is just borderline. They may be either positive or negative. And in this case, this query compound is close to negative compounds. So here GM value will be high negative and RA function will be low. Now for the previous 5 models, for 5 endpoints, we have done the SHAP analysis to understand the relative importance of descriptors towards prediction. And we have seen that in most of the cases, we find the Russell descriptors most important for predictability of or prediction in comparison to the original structure and physiochemical descriptors. So here, which chemical or structural descriptors we are using, whether they may be 2D or 3D or anything, that is not important because we can calculate Russell descriptors from any kind of descriptors. We can calculate from fingerprint, we can calculate from 2D descriptor, we can calculate from 3D descriptors. But the question is whether they can improve the quality of prediction of test set or not from the same level of chemical information, and whether they are more important than the original chemical descriptors or not. As you can see here, the RA function is the most important descriptor here from the SHAP analysis, and log P is here, which appears to be much less important than this. But of course, the RA function has information from log P. But as a whole, this latent variable RA function statistically shows more importance than the original physiochemical descriptor. This happens every time. Here also, Russell descriptor is more important. Of course, here the original structural descriptors are more important, but the Russell descriptors takes place 3. These are the SHAP analysis for the rest 2. Here also you see the average similarity, the second most important descriptor. And here the Russell descriptor is somewhat less important in this for this particular set. So not always that we are getting Russell as the most important one, but it is true that Russell approach is increasing the external predictive quality of the model from the same level of chemical information, as can be seen from statistical analysis. And also we have verified this from 20 times repeated 5-fold cross validation, and for the 5 data sets, we as we have applied the same set of same combination of features as with original chemical descriptors for different machine learning methods also, like linear SVM, random forest, PLS, regression, and MLR. And finally, we found that in the machine learning methods like RF and SVM, we got more fitted model for training set. But when you see the predictive ability for the test set, we got MLR as the most predictive one for the test set, as evident from the ME for value for the test set. Now, this is the third case study, application to cardiotoxicity data. This is still unpublished. So we have collected the cardiotoxicity data and the usual data calculation, descriptor calculation, data treatment. We have divided them into training and test. We have selected features, and then we have calculated Russell descriptors. Then we have done data fusion. That means original structural physiochemical features plus Russell descriptors. Then we have gone for feature selection. Then we have done a applicable domain plot using the novel DTC plot. Then we have gone for partial least squares modeling. We have additionally done different machine learning methods, regression, linear SPR, support vector regression, random forest, gradient boost, and boost, MLP, and KNN, and we have done prediction for the test set. Okay, this is the GTC plot. This is a plot where we show the absolute difference of the response values of the first 2 closed source compounds for each query compound. So as we go up, that means the difference between the first 2 closed source compound increases. And when you see the black bubble, the bubble size indicates the difference between similarity level of the closed source compounds. So if the bubble size is high, then obviously you may remain in the higher zone, that means in the top position of your plot. But there will be a concern when the bubble size is small, but still you are in the higher side, at least more than the 1 unit here. So those are the points of concern, like this, and also like this. This can also be a point of concern, but here we have identified we wanted to identify the least number of compounds as outlier, and we have omitted these two. Now these points, these are also small points, but as you go towards the right hand side, the level of similarity actually decreases, and here the level of similarity is so low, the near 0.02 or something. So the impact is very less, so we have not considered. And this is the PLS model, and this has been presented like this in a clockwise manner. When you start from here, this is the most important descriptor, RA function, then block P, then the state, then the atom pair, and it goes on like this. So from the VIP, actually RA function, that is the Russell descriptor, is the most important one. And this is the quality of the model. This is the external prediction quality, Q square F is 0.660. And this is a VIP plot. As you can see, the RA function is the most important one, which is more important than the physicochemical descriptor. And this is a scatter plot. So we have identified some outlier from the training set. This may be due to the long aliphatic chain, and this may be due to large number of the electronegative compound in the small size. And this is a comparison of quality of different models. As you can see, if you see the 20 times 5-fold CV value, the R square value is the mean value. You can see that from yes, I think for random forest is the maximum 0.554. For Metabush is 0.56, which is the maximum. What is the previous one? Here is 0.508. This is the value of cross validation from 5-fold cross validation, repeated cross validation. So in the training set, we get the maximum value in the ADDMC. But if you see the test set prediction, in that case, okay, the case test is here. So this is the MA test, and the ADDMC MA test is high, 0.49. But if you see ALS, it is only 0.4. Breath reduction is almost same, but the linear SPR shows higher value. So based on the test set prediction, actually PLS appears to be the best one here. And with the same set of descriptors, we have also performed classification-based modeling, and so we get quite satisfactory results using Russell descriptors and with the. So based on our best PLS model that I've already described, this is a tool to calculate the heart channel toxicity from a given compound. It can calculate the value based on the PLS model, and also it takes into account the AD of the model for the query compound. So this is already available in our site. Now, based on these studies, actually we have developed several tools which are available in our website, which can be freely downloaded. And most of the tools are Java-based tools. And along with these ones, we have also included this machine learning regression GUI. This is based on scikit-learn library. So the first three are Java-based, but this is Python-based. Last one. We have also applied Russell for modeling other endpoints, like in material science for prediction of specific surface of perovskite, but I'm not describing here because of lack of time. Also, we have applied this for nanotoxicity prediction, for prediction of cytotoxicity of TiO2 based multi-component nanoparticles. So based on these studies, I'd like to conclude that using simple structural physiochemical descriptors, we can develop quantitative predictive model using the raster approach. So raster descriptors are computed based on the usual structural and physiochemical variables, but using this similarity-based approach, we can enhance the predictive quality of the query set. It suggests that they have potential to give predictive models, and they can enhance the quality of prediction with the same level of chemical information. And also based on this study, we have proposed three important similarity-based function, RA function or RA score, GM, and average similarity as important descriptor for raster approach. So we have got funding from SCRB and LSRB DRDO. Okay, for more information on raster, QSR, and chemical information in general, this is the upcoming book. It is not yet published. I think it will be published by June. And all our tools are available in this site, and there are also some other sites where we have some other QSR related tools. So one can go to these sites and download those tools free of charge. Thank you very much.
Thank you very much, sir, for a wonderful talk. We can take a couple of questions if there are any from the audience present here. Any among students?
Yes, please.
Yeah, sir, please.
Thank you for your talk, sir. Sir, what I wanted to know is the read across descriptors that you use for the toxicity endpoints.
Not only toxicity, it can be used for toxicity, activity, property, or whatever. And as I mentioned, the type of descriptor, original descriptor that you are using is not important. You can use fingerprint, you can use constitutional descriptor, you can use topological descriptors, you can use quantum chemical descriptors, you can use geometrical shape based, whatever. For every kind of descriptors, you can calculate RASA because it is just similarity based approach. And it is also not important which modeling strategy you are using. You can use simple MLR, you can use PLS, you can use classification, or you can use the machine learning algorithms, whatever.
Right. So what I wanted to know is the data sets on which you benchmark your read across descriptors. What is the structural diversity of those molecules? Are they compounds that belong to the same series or the same class, or are they diverse in nature? Because sorry, please go ahead.
Yes, for some of the studies that I mentioned, for some of the cases, the data set is not that much diverse, like in titanium dioxide case, I think this one. This case, the diversity will not be that much because this is based on metallic oxide. So in this case, the chemical domain is limited. But for some studies, like your heart channel, the chemical diversity is very much high.
Does it perform these of compounds and better on a diverse set, or there is no difference? I mean, I'm trying to ask.
It can be used for a structurally narrow domain also and structurally diverse domain also. But read across may be very suitable for smaller data set because you know, for smaller data set, if you develop a statistical model, the degree of freedom will be low. So we cannot get a statistically meaningful model because, as you know, for the validation of the model, you have to divide the data set into training and test. So you are losing some information. So you means say you have very limited number of data, 30 compounds. If you go for dividing the 30 number of data, compounds into training and test, say you have 20 plus 10. So training set is further narrow. So you don't get a structurally meaningful one. But if you do read across, you can get good quality of prediction. Now, in case of RASAR, although this is QSL-like, but there you are using, say, RS score, that's a latent variable-like descriptor. That means it contains chemical information from multiple descriptors, but you are using only one descriptor. So in that way, you can increase the degree of freedom. So it may be suitable for smaller data set.
Just one. So you presented different metrics when you compare 2D QSR versus the read across. So which metric do you think is the most important when
error-based metrics? Because it is wise not to use correlation-based metrics like Q square F1 or R square, because in that case, there is a point of reference that is Y bar of training. So that depends on the range of your data set. So Q square F1 can be misleading sometimes. So it is better to use error-based metrics like MAE or RMSE.
So first thing that I like to tell you, really very nice work, and I think CubeSats are, you know, but RASA is new for me, and a lot of new things you are doing, and especially I got interest cardiotoxicity because I'm working on this topic.
Okay.
So, and most of the drugs they fail because of heart toxicity, and long QT is the main problem. So, but there are a lot of other drugs are there, like anti-cancer drugs, but a toxicity by different way. So when you make these tools, like, you know, so what is the first source of your drug molecule? Like you choose from the known data sets that which are already heart toxicity, look the structure and make that, you know, those RASA, the scoring, all this. And then
yes, this data set we have taken from the known. Actually, we have used this as a previously also, but here we have used just to show the importance of RASA. Here, the heart channel prediction is not our focus of research. Our focus of research is that when you use similarity-based descriptors along with the chemical descriptors, it increases the quality of prediction for the query set. That is that we are addressing.
so any kind of cardiotoxicity can be tested here because it may not be target, may not be heart.
No, this is only for heart.
So are you considering to put in some more data which are not through heart? And let's see any chemical similarity structure for cardiotoxicity.
As I mentioned previously, I think
Please check. The slide is not.
disconnected, I think. Yes, actually we can use multiple target. This concept is there. We have not used yet, but it can be done. Multi-objective model, that can be done.
Yeah, that will be good. Actually.
Yes.
Because any compound can be looked into.
Yes, it can be related to the several molecular initiating events in the adverse outcome pathway. That is there. Yes, it can be done.
Okay, thank you. That was my question.
Kunal,
So one more question.
now, as far as the cardiotoxicity prediction is concerned, the heart toxicity, you said you have already incorporated a lot of chemical information as well. Say something like there are particular substructures which are more prone to show cardiotoxicity, like especially heart channel toxicity, including say a piperidine ring or suitably a cationic nitrogen and suitably located aromatic rings. So in some way, can this say after the prediction, if the prediction is high, can it in some way highlight the structural alert? Is
Yes,
it possible?
yes, structural alerts you will get from, as you can see, the usual your E state or the constitutional descriptor. You have the idea about the structural requirements for enhancing the toxicity. That is there. That is already there because we have already modeled this set, I think, 10 years
For
back.
a query compound where the prediction is already
Yes.
high. So when you are giving the quantitative predictions, some number, say a probability of the cardiotoxicity or some number. So in that case, can it also highlight or give some indication as far as the structural alert present in the query compound?
That is
Because of which
that is already given by usual QSL. Now from usual QSL that you can already get. Here we are using some similarity-based descriptor just to enhance the quality of prediction. Here the objective is different. The question that you are asking, that information can be obtained from the usual QSL descriptors. Here we are using the RASA descriptors to enhance the quality of prediction and to explain the prediction behavior of some query compound, how similar they are and to which source compound they are similar. In that way, we explain.
Thank you.
Now, in toxicity modeling, okay, how important is nonlinear modeling? Because all of our ML methods are strongly biased toward. But I noticed that you had an MLR.
Yes.
You know,
Yes, I would like to answer this question because in the like these descriptors, you can see the initial slides. You see, when I derive this descriptor, the RS code, that is a latent variable from multiple descriptors, and there is a nonlinear function here. So when you derive this descriptor, the nonlinear function is already there. And when we are using this in the final linear modeling framework, is working very good. So, and sometimes the quality of prediction is better than the nonlinear.
so if I use the ML methods, I already have nonlinear descriptors and then I already have nonlinear modeling.
Huh.
I have nonlinear modeling. So now my equation is getting very complicated. I have nonlinear descriptors and over that I have a nonlinear model.
Most of in the linear modeling framework, you get the equation. You can see the equation. You can get the contribution, quantitative contribution, either positive, negative. You know that is the contribution. And as we also marked with the original descriptor, so in the same equation, you have contribution of log fit and also contribution of this Russell function, both. And this is transparent, and anybody can reproduce this because you have the equation.
Thank you.
Okay, I'm sure there are more questions, but we can take it in the breakout sessions. I once again thank Professor for taking out your time and visiting us in person. I would like to invite Professor Tamilvanan and Dr. Sanjay Banerjee both to jointly felicitate Professor Roy.
Yes, sir. Yes.
So all of them are from the same university.
I think I know Dr. Kunal from my bachelor degree, master degree, PhD.
And also when you were in
Yeah.
Delhi.
All the time I'm in touch with him and I observe him, and he is the top rank in India when we giving a list of top 2% list. I was so happy that, from Jaratpur University, very small university, sitting there, his rank is too high and he's visible whole India. And his contribution is really, really very high. And I've seen him, his master and PhD when he started synthesis and slowly moved to, he's doing QSAR, I know, but he's done a fantastic job last several years. Very happy for him.
Thank you very much to all once again. Please take your seats. We move along and have the good fortune to have the next speaker as Dr. Madhvi Sastry from Schrodinger. She is a senior director there. And she is a world-renowned expert who has contributed significantly in the development of Schrodinger suite of softwares and continues to do so. And also she is very much excellent teacher. And when we visited last time NITS Jorat, she helped us clear some of our doubts in molecular dynamics and other topics. So we are lucky to have her. Madam, are you able to hear us?
Yes, I'm able to hear you, but can you hear me? Yes.
Yes, but yeah,
Yeah.
yes.
So thank you, Vaibhav, and thank you, NIPER Guwahati, for giving me this opportunity to talk to different scientists and students from both master's, PhD, and further studies that everybody here in the audience is doing. Thank you much for giving me this opportunity to speak. So today I'm going to talk about some work that I have done uh, with respect to human carbonic anhydrase, which is a collaboration between industry, academia, and I'm going to just talk about a few highlights of the study. But before the study by itself, I'll give you some basic level understanding of what is this waters and protein cavities. So we all know that water is important and it is there everywhere in biology. And most of the protein bindings are so. My talk is very much tailored to drug discovery. So I'm going to talk about protein targets specifically. So protein binding sites are, we all know that are filled with water, and water is a direct competitor in ligand and substrate binding. So whenever the protein cavity is filled with water, if a ligand has to enter the cavity, it has to remove the water from the cavity and throw it out, desolvate the cavity. So water is a direct competitor. And some of the waters, when they get into the protein cavity, become very unstable. So we need to remove those unstable waters. And why do they become unstable? I'll let you know in the next few slides. But water energetics cannot be determined from structure alone. Just by looking at the crystal structures of the proteins, you cannot understand the energetics of water. You can just see the waters, have some very vague understanding, but the energetics cannot be determined. For determining the energetics, we need to do some quantitative methods. So I'll be talking mostly about water and ligand competitor binding, competitive binding, I would say. So I'm talking about this method where you can actually um, calculate the position of waters in a protein cavity. This is a cavity of a protein called thrombin, an oncology target. And what we can do is we can actually predict the waters in the pocket, number one. And number two, we can predict the thermodynamics of these waters. So when I say you predict the thermodynamics, we all know that thermodynamics is determined by the Gibbs free energy change. I hope you all have heard of this in some course or the other, either in your intermediate courses or degree courses. So delta G is what determines the stability or instability of any process in this world. So with respect to waters and protein cavity, when we say we find whether this uh, waters are happy or unhappy, what we basically mean is the water more stable in the bulk, or is it is it more stable in the pocket of the protein cavity? So if it is stable in the pocket of the protein cavity relative to the bulk, we call them happy. I'm just coloring them in green. You can use any color that you like. And unhappy waters are those which are not stable with respect to the bulk when in the pocket. So this is like a GPS. It's a map. So we call it as a water map. So now, for example, how do we use this in drug discovery is, this is a protein cavity of thrombin, and these are the waters in the cavity that is predicted by in silico molecular dynamics methods. And when all the green ones are the water is not content, it prefers to stay in the bulk. Now we have a small molecule here which sits in the pocket. When the small molecule comes into the pocket, it displaces these molecules, but it is not displacing the red molecule, which is the unstable water, or I would call it an unhappy water. So the potency of this ligand is 10,000 nanomolar. Now, when we go to the next step, we have a halogen substituent to this hexyl ring, the benzyl ring. You have a halogen substituent. This is just coming closer to the unhappy water, but it's not really displacing it. So the potency has increased a bit more to 9,010 nanomolar. So these are the IC50 values. Now, when we go to the next pocket, the fourth pocket, we have a substitution in the top, and the phenyl ring is a bit down in the pocket, and it is reaching closer to the red unhappy water. So the potency has increased from 9,000 nanomolar to 654 nanomolar. And then from here, you go to the fifth cavity. In the fifth cavity, we have a ether substituent here. And in this ether substituent, the carbon or the methyl group of this ether linkage is coming very close to the red water when it sits in the pocket of thrombin. Thrombin is a protein, as I said. It's an oncological target. And so now the potency has gone to 89 nanomolar. So from 654, we have reached a very high potency of 89 nanomolar. And when we make this particular substitution, where we have this thiol ring, the 5-membered ring with sulfur here, this yellow color is for sulfur, and a halogen substituent, this particular water is displaced. It's being kicked out by the ligand. And this unhappy water, when it is thrown out of the pocket, it adds to the potency of the ligand, because you are removing a structure from the pocket, which is very leading to the instability of the whole system. So the full displacement corresponds, one, to a very tight binder, that is, this ligand is basically occupying the pocket. Additionally, it is throwing out this high energy water. So this particular ligand is seen to have a potency of 3 nanomolar. So now you see, using this particular GPS of waters in the thrombin pocket, we see how you can design ligands in such a way that it increases the potency of the ligand by displacing these unhappy or unstable waters. So using these waters, we can help design molecules or drugs which can bind, or potential drugs, I would say, bind to the pocket of a particular protein target. But remember, waters are not the only things which can determine the potency of the ligands. There are other factors. Waters can be used to determine the potency only for those situations where you see a very hydrophobic pocket, and there are no other interactions which are determining the advantage of one ligand over the other. Okay. For example, let us look at the thermodynamic decomposition of ligand protein binding. So initially you have a solvated ligand like this, and a solvated protein, apoprotein, which doesn't have any ligand in the pocket. Then the solvated ligand gets into a bioactive conformation. Similarly, the solvated protein gets into a ligand-induced conformation. It just gets into a conformation which can adapt, or which can take the ligand inside its pocket. then the ligand gets desolvated. That the ligand comes out of the water, it's entering into the protein. Similarly, the protein cavity is now getting desolvated so that it can throw out the waters to accommodate the ligand inside, and then the protein ligand water complex is formed. So the final delta G of binding, the binding potency in a way, is the sum of all of these individual delta G steps. Delta G of solvated ligand to ligand in the bioactive conformation to desolvated ligand. So each of the delta Gs that you see here, if when you sum them up, is what you get a total binding free energy. So water map is taking care of this part of the entire thermodynamic cycle. This red box that is there here. So this is what is where the solvated protein is getting into the ligand induced conformation, and this is the component that water map deals with. So to identify theoretically the binding potency of a ligand, we need to consider all of these components. But I'm talking of a situation where this red component here plays a major role. I'm going to talk about a system called as human carbonic anhydrase. Now from here, so what does the method by itself do is it basically runs a MD simulation for a 2 nanoseconds with waters. So the simulation is done on the waters and the protein is kept more or less constant. It is restrained from movement and only waters are kept movable in the pocket, and a 2 nanosecond molecular dynamic simulation is run. Then all these waters across the trajectory are clustered into groups depending on their spatial location. Once they are clustered, then you take a representative of each water cluster in the pocket and calculate the entropy and enthalpy for the representative water, that is the hydration site. From now on, we'll call it as the hydration site because this is a representative of the cluster of waters. And then all the energy terms for each hydration site that I'll show you is with respect to the bulk, because free energy by itself has no meaning. We are talking about the difference in free energies, not just the free energy. So when you're talking about the difference in free energies, you are considering the free energy of a system with respect to something else. So the difference between the two is what we are considering in the entire study. Now we use inhomogeneous solvation theory to really calculate the entropy. Now I will talk about this in the next slide. So now, generally for water, so delta G, is delta H minus T delta S. Here you see in all of these delta H and delta S. There are two components to calculating the binding free energy, the enthalpy change and the entropy change. The enthalpy change in all of these calculations comes from the force field that we use to run a molecular dynamic simulation. Whereas the entropy doesn't come from the force field. So we need to have a way to calculate the entropy. And that is the toughest part in this whole thing. So how do you calculate the entropy? So again, let me get back. Delta G is equal to delta H minus T delta S, the Gibbs free energy change. So entropy is the problem. Delta H is coming from the force field. So we do a sort of a water distribution functions. So all of these are distribution functions, Boltzmann constant. And then we do a representation in terms of mixed quaternion Euler angle method, so that becomes easy to solve those equations. You really don't have to worry about this math that you see here, which is horrible. I understand most of you are from pharma background. You don't have to do all of these integrals or calculate all these angle distributions and integrations, summations. What we basically do is the entropy is calculated like this. It's calculated as a pair correlation function wherein, let us say this is the pocket of your protein cavity and you have a water at the center. You calculate the distribution of the water around this water molecule at different distances. So when you say R, let us say dr that you see here, R is the radius. So from this water, you calculate the distribution of water, let us say within 1 angstrom radius, then 2 angstrom radius, calculate the differences. Likewise, 3 angstrom radius. And then we calculate the number density, the particle number density, which is nothing but you divide your total count by the total number of molecules, the number of waters within a particular distance, you divide it by total count n. You divide this number by 4 pi r square dr, the volume of the spherical shell, and then divide this by the particular number density. Basically, it is a very simple calculation, and this particular value will give you the entropic contribution to the delta G. So delta G equal to delta H minus T delta S. The delta S term comes from the water distribution and the particular number density that we calculate from a distribution of waters across each water molecule. Likewise, next time you take a different water site and look at the distribution and calculate the pair correlation function. So it looks like a very intensive maths, but it's actually not. It's a very simple math, just looking at the number of water densities and the pair correlation function. And this is done only to calculate the entropic contribution. And once you get the entropic contribution, we calculate the delta G of binding. Again, this looks like a very mathematical equation. Again, it's not. It's basically what we are doing here is all of those waters which are within a particular distance of a ligand, only the delta H and delta S of those water contributions are added to calculate the delta G. So these are nothing but the step functions. So the distance at which a ligand atom begins to displace a hydration site is RCO. So any of the water molecules that come within the RCO, we take the contributions of delta H and delta S or delta G from them to calculate the delta G of each hydration site. Now, this is as far as the theoretical background is concerned, all of this that I have been telling you. So there are many things that WaterMap can address and has been used in several publications on serine 3 proteases, calculating kinase selectivity. The advantage of this technique is it's very sensitive to structure. So wherever you find that two proteins have similar cavities, very similar, and you want a ligand to bind to one protein but not to the other, especially where you're looking for selectivity. In those situations, since the method is very sensitive to structure, it will be able to pick that particular selective molecule and has been used for kinase selectivity. It's been used on GPCRs, kinase binding, PDZ domains, falcipanes, and many other different type of targets. For example, I used it for my studies as well, internally as well as for the publications. Using this technique, what we found is that I'm talking about a situation which is a real life scenario. Nimbus Therapeutics is what is our very strong collaborator, I would say, or a partner with Schrödinger. So we started with 1.3 million molecules. And then the largest potency that we could get in ACC target is about 8,000 nanomolars. And then we took these compounds, reduced them to 5,000 IDS, I'm just giving a very broad picture, and then synthesize total 175 compounds of these 5,000, and we got a potency of less than 10 nanomolar. And then out of these compounds, we again came up with 10,000 ideas, ideated, of which synthesized 2025 compounds, and then got a potency of less than 1 nanomolar, all within 16 months. That is about 1 year and 4 months approximately. So we could get something which used to take years, we could get to it in 16 months by also synthesizing very few compounds. This is just 175 plus 225 compounds that we have synthesized, not so many compounds that you see on the top. So synthesized very few, and since the in silico methods were applied, the whole process also got speeded up very fast. And then we received we achieved several milestones by also confirming the X-ray binding mode through crystallography, and then in vivo target engagement, and also in vivo efficacy, and now human trials. So the thing is, using very efficient in silico as well as, experimental methods, one can try to get to find out drugs for a particular disease very fast and at very low cost. This was published in PNAS, and you can actually go ahead and see that. I'm talking about a situation of human carbonic anhydrase. Um, um, Vaibhav, how much time do I have? Hello? Hello?
Ma'am, another 10 minutes.
Okay, so sorry. Yeah, just a moment. So I'll do it in 10 minutes, I say. So this is an application to human carbonic anhydrase, where, carbonic anhydrase catalyzes the reversible hydration of carbon dioxide. And this defects in this enzyme result in osteoporosis and renal tubular acidosis. So for this target, water plays a major role, and we need to understand the balance between entropy and enthalpy. And the study was conducted to analyze water networks where ligands displace some waters, whereas they perturb some other waters. That is, some waters go out of the pocket and some waters just relocate within the pocket. And then we quantify water energetics here. So the objective is to examine effect of water rearrangement. This is a very experimentally well-defined model system, especially our experimental group are experts in this particular target. So it was easy for us to do all the in silico methods in a way that we understand the whole system or the science behind the whole system. So the binding pocket of human carbonic anhydrase was done using ITC. The X-ray crystallography was done by a collaborator, and MD simulations water map was done by us. And we try to understand water rearrangement due to mutating the residues of the pocket, also placing Hofmeister ions in the pocket, so that we can see, can we use this as for understanding the strategy of designing ligands for this particular target. So we have used using sequence analysis and stuff, we found out we decided on which are the mutations that we should study. One is a phenylalanine 131 mutation to tryptophan and tyrosine, likewise a leucine substitution to alanine, and valine and aspargine and threonine with two different ligands. So TA and BTA, benzene, thiazole, sulfonamide, and the thiazole sulfonamide. So these are the two ligands. Both differ in one extra phenyl ring here. Okay, so that helps us to understand quite a few things in the pocket, and I'll talk about that. So first of all, before we even do anything, we had to understand whether water map is able to, we need to validate whether the technique is able to reproduce the experimental results before we use the technique further for prospective studies. So we had the experimental results of binding affinities from ITC, and the dotted lines are the water map results, and the solid lines are the experimental results. And we found that the calculations are tallying very well with experimental results, which we published in 2017. So the first validation was done, and we found that there's a similar trends between the theoretical and the experimental results. After this, what we did, so what was happening in the pocket is we used the wild type pocket, and the waters were distributed like this that you see here, and then the pocket with the ligand, the benzene thiazole sulfonamide group here. And we see when the uh, benzene, the ligand is bound to the pocket, we see that so now there are two mutations, a wild type and a leucine 198A. And in the mutated pocket compared to the wild type pocket with the ligand, we see that the cleft here enlarges and two different extra hydration sites come in when compared to the top right panel. So you have the ligand in the wild type and the ligand in the mutated leucine to alanine type. In both of these situations, we find that the cleft is enlarged. Of course, that is expected. So the water network is expanded, and then the waters in this network undergo an enthalpically unfavorable rearrangement. The numbers that you see here, 3.9 and 1.3, are the entropy contributions. I'm sorry about that, enthalpy contributions. So the enthalpic properties of these waters become very unfavorable. So there's an unfavorable rearrangement. And because of this, we need to consider how to actually tackle this situation to get a situation where you have all favorable waters and the unfavorable ones are removed from the pocket. Similarly, we looked at a double mutant, L198A and F135. For all of these, we have crystal structures. And the PDB IDs, I have forgotten, we deposited them in the protein data bank. But when we looked at understanding the water networks in the cavity between the wild type and the double mutation with the two different ligands. Now, there are three parameters here, the wild type pocket, the double mutant, as well as two different ligands. This is TA and this is the BTA. What we found from all of these calculations here is that mutations enlarge a cleft in the non-polar wall. Even though this mutations, one of the mutation is a similar size mutation, it enlarges the non-polar wall. The water network is expanded here because of the mutations here. So you see the wild type here, you see the mutated one, still you see a enlarged water network expansion, which is not intuitive actually. You don't expect that. But here we see that. And when BTA binds, the benzyl ring forces an enthalpically unfavorable rearrangements of its constituent waters. So the resulting is a hydrophobic effect and is entropy driven. So we understood that these waters, when we do a mutation as well as increase the size of the ligand, is leading to enthalpically unfavorable waters, which need to be pushed out of the cavity. So a strategy to enhance the affinity of bimolecular interactions is what we came forward with. So enthalpically favorable rearrangements and perhaps the binding pockets of other proteins gave rise to stronger protein ligand association. So the nature of the correlation in this system and our ability to attribute it to primarily to the influence of mutations is unique. So how is the mutations in the protein affecting the local water networks is a very unique way of looking at it. I'll also come back to one of the slides. I think I have another 5 minutes. I'll be able to finish this. So mutations that decrease the hydrophilicity of amino acids particularly are likely to increase its affinity of ligands. So this is basically what is one of the strategies. So you need to do a mutation with the hydrophobic amino acid residue, and accordingly, by reducing the free energy cost, the rearranging those networks during binding, when all else, the conformation of the protein, the van der Waals interactions is all equal. So basically what it means is we have to look at the mutation such that that decreases the hydrophilicity of the amino acids. Next, we looked at the Hofmeister ions. So we see that these ions induce structural perturbations and are likely to be sensitive to local environment. Carbonic anhydrous has a zinc ion in its pocket. They trigger rearrangement of waters beyond the first hydration cells, and ion-induced structural perturbations are likely to be sensitive to local environment. So this is what we are going to study in the next, which I'm going to do it quickly. So what are Hofmeister ions are? There are two types of ions. They can be divided as cosmotropes and cheotropes. Cosmotropes ions in the pocket stabilize the folded proteins. They're strongly hydrated and small in size, whereas cheotropes, they promote denaturation of the protein and enhance the solubility of protein in solution. They are large and weakly hydrated. So for people who don't know what are cosmotropes and cheotropes, this is a broad definition. By hydrated, we refer to free energy of hydration. Earlier studies on ions in bulk water suggest that effect of ions on water structure is limited to first hydration cell, whereas we found in this study that it goes beyond the first hydration cell. The effect of studies in the protein, when the ions are introduced, it goes to a very large distance, whereas in protein, the water structure, the effect of ion on water structure is not limited to the first hydration cell. It goes beyond the first hydration cell, very much different from bulk. This is basically what we have found in this study, and that was basically the objective. So how do ions of different charge, topography, functionality alter the structure of water in the protein cavities? These are the cosmotropes and these are the cheotropes. This is the pocket of the human carbonic anhydrase. And what we found here is, this is one of the ions, iodine. I'm showing the example of a cheotrope, which is iodine, and iodine in the pocket. And when we remove these iodine, this is filled by two water hydration sites. These are the enthalpically and entropically unstable waters. So what it means is you can use these ions to displace unfavorable uh, hydration sites. And as a result, that can be used for designing whatever we want to in the future, depending on our requirements. So these are again the contribution of anion induced rearrangements. This is a slide which we published in 2015, where we were mostly trying to see whether, again, validate with ions whether the method is working and is in sync with the experimental ITC results. For example, thiocyanate is an ion which triggers rearrangements of water up to 8 angstrom from its surface, which is not so in the bulk. Bulk, it just triggers rearrangements to the first hydration cell. After this, we did some modification to ligands. We went beyond the BTA and TA ligands. We found a very unstable hydration site here, and we tried to design ligands which displace this particular unstable hydration site. Each color is of a different ligand here. And then we did a free energy perturbation calculation, FEP, and we found that the experimental values and the theoretical values, predicted values, could distinguish between C alkyl site groups, the, the ligands that had C alkyls versus ligands that had N alkyls. The C alkyls are the cycloalkyls, N alkyls are the normal chain, and we could see the methods basically are able to, first of all, predict and also use for prospective calculations for our own design of ligands. I mean, this work is at this stage currently, and we need to take it forward. And the conclusions for this whole study is mutations tend to make the enthalpy less favorable, but not the reverse. A reversed form of enthalpy entropy compensation could result from mutations that weaken the network of water. Two mutations most likely cause such an effect, that is N67L and versus phenylalanine to tryptophan. And ion-induced structural perturbations are likely to be sensitive to local environment influences. And using these studies, whatever we have understood about the HCA2 pocket from these studies, we went ahead to design a few ligands and also got the crystal structures of those. And I should acknowledge the Schrödinger team with whom I was working closely on this project. And of course, the Harvard team who were doing all the experimental data for us, and Dr. Vaibhav, Professor Yasen Murthy, and the NIPER Guwahati organizing committee. So thank you all for giving me this opportunity.
Thank you very much, madam. So kind of you to spare time for us. And now I would like, if there are any questions from the audience, we can take one question. Okay. If there are none, then I would like to invite Professor Coutinho to in silico felicitate madam. Madam, these are our token of appreciation. We will send over to you to Jorat possibly. So we move over to the next speaker. We have we are fortunate to have one more friend of ours, Dr. Devendra Thakad from NIPER Kolkata. He is faculty in Department of Pharmacoinformatics there, and he specializes in chemoinformatics tools and machine learning for drug discovery. And without wasting too much time, I would like to invite him, please, so that we can also have lunch as early as possible. All depends on him.
Okay. Yeah, thank you, Weber, for this kind introduction, and I also thank to NIPER Guwahati and Dr. Weber for inviting me over here. Yes, already. So, hello everyone. So today I'm going to give basics of what is the theme of informatics, what are this, rather than beginning of the theme of informatics. This term was recently coined around 20 years before, though work related to the theme was started around 1960 or 1970. And when people started in the area to how to solve it, how to predict the activity of a given compound, and how to manage those compounds, how to store it, how to retract them, how to search. Different definition for the chemoinformatics, and one of the guy over here, this John Gester, edited NIPER, Mohali. So he is one of the well-known chemoinformatician. In which term we can say application of informatics to solve the chemical problems. We can say this is a multidisciplinary area or field, so that include, we can say, different subjects, whatever listed over here, different computer science, biology, chemistry, drug discovery, medicine, mathematics, biostatistics. The name game, spelling and terminology. So different people have given different terms, what to use. They have different opinion. So we can see what they have used. Cheminformatics, chemical informatics, chemi-informatics, molecular informatics. But if you check the literature, you will see chemoinformatics is the most commonly used, but these are also in the second, third, fourth positions. So how this field is different from bioinformatics? What is what we have? DNA, RNA, proteins, their structures, and we have the building blocks for them, bases and amino acids. So we have some repeating units, right? But in the case of the chemical structures, what we have? We don't have any such repeating units. We see the history where people were trying to address such type of the research work. So American Chemical Society, 1916, they started this journal. Journal of Chemical Documentation. Then they changed the name of the journal. Journal of Computer Science, and it was up to 2004. Sorry, yeah. Then in 2004 they started JCIM, Journal of Chemical Informatics and Molding. But by different publishers, they start another journal, Journal of Chemoinformatics. And there was one more journal was the Molecular Informatics to publish research related to the chemoinformatics. So what we do in this field, what we can expect, how to represent the molecular structure, how the computer can understand the chemical structure, how we can see similar molecule or different molecule, how to do chemical search, complete chemical search, substructure search, how to decode the molecular structure to a computer, how to convert the normal structure to a hidden structure, and how to generate multiple conformations, and different algorithm to understanding the stereochemistry, aromaticity, other stuff. And big thing is the chemical reaction, how to present the chemical reaction to the computer, and if we can represent how to differentiate one type of reaction to other type of the reaction. And if we represent, and then how to search for those type of the reactions. So chemical data, old school, when there was no internet, no electronic stuff was there. So you have to go for searching for any articles, you have to go library. So where you have to see long books, long list of the books. So this is the one of the collection of the chemical abstract published by American Chemical Society. You can see this is the 10th index, more than 75 volumes, and you can check what are the different publisher, different titles, and they have got more than 24 million structure in this collection. So that was the old time. Now they have converted, they made one unit class, and they electronized all the stuff available at that time in the form of the sci-finder. Here you can easily search anything what you want, what is the reactant, what is the product, reagents, solvent, catalyst. We can skip this. So that was the first, we can say, one kind of the chemical database people have started, especially American Chemical Society. In addition, there were other groups or companies, they also started different chemical databases, Cambridge structural databases. This is the database collection of the small X-ray structures. So where all the structure mainly solved by the X-ray crystallography, or sometimes by other method like with protocols. Then you see some other small chemical databases. This was the first very big publicly available chemical database, developed by the NIH. Now it has got more than 120 million chemical structures. And here I have compiled the different collection of the around 40 different chemical databases that I have used for my work. And here you can see their wavelength, and you can explore what kind of molecule they have, whether those are the building blocks, metabolites. So we have used those different type of chemical or databases to analyze whether those different chemical databases has got a atomeric duplicates. So that work we will submit to the JCM very soon. So currently a copy of this is available in the CHEM archive. How do we represent molecule in the computers? That's very important. As per our requirement, what we want. Just we want to enter name of the molecule, or we want to draw, or we want to build a molecule in the form of the XYZ coordinates or gen matrix. Or we want information about the different connectivities between the atoms. Or we want to go beyond the connectivity, what we call orders. So based on what we want, we can store different kind of information for a given molecule. And based on what type of the molecule we are storing, we can have different type of the information. Just name, we have the very minimal requirement for storage. This is 2D drawing, what we do in the computers, drawing the pen, draw notebook. But if you want more information, we have the 3D structure. We have the relative orientation of different atoms in the space. If we want more information, we can go beyond the 3D, and we will have more information about like molecular electrostatic potential or the molecule. And there are several other beyond the 3D, 4D, 5D, 6D. What are the component of chemical structures? So many information we can store about any chemical structures, the molecular formula. Just we have to determine what are the different constraints. So it tells about what are the different constraint elements in what proportion. But we want to store more information. We have to take information about the connectivity. What are the neighbors of particular atoms? If we want to perceive the bond types, so we have to, of course, understand if there is any aromaticity. If there is a stereochemistry, of course, that is very important. We have to take care of that. So we have to define those very simple molecule, phenylalanine, and it can be present in the ionic form. That we can also store. If there is any isotopic central gem, that we can also define in the chemical structures. And if we want more information how different atoms orient in the 3D space, then we can of course use the 3D structure of the molecule. So if we visit any chemical database, we have the 3D structure, but only one confirmation of a particular molecule is available. But one molecule can have the thousands or thousand different confirmations that you have to generate your own. Rarely any database provide any collection of different 3D confirmations. So molecular formula, just we have seen, we can skip it. So traditionally people have used the tribal name to name any molecule, like this synchronoderivative molecule for the malaria. They call it quinine, right? If you discover some molecule in the medicinal chemistry lab, you will give octane, hyperbody, 010 to something, or like benzene was derived from the similarity to benzoin. So this is the molecule. This is a physically interlocked molecule. There is no bond. There are 5 rings which are interlocked with each other. And if we represent this topologically, it looks like a Olympic symbol. So that's why its name is given Olympic day. So if you give any IUPAC name for this molecule, it won't be useful and it will be very difficult to use that name. Similarly, there are several other physically interlocked molecules. You cannot use their IUPAC name to describe. It is better to use a tribal name or generic name. The IUPAC just has given some set of the rules by which you can easily number and define the. You can give some unique name to a molecule, but sometimes you may from one molecule can have the multiple IUPAC name. And the size of molecule increases, sometimes the length of the IUPAC name may be very big. So it is very difficult to copy paste search use. So it is advised to use something else. Like this molecule you see, what is my name? I don't know. In center, you see benzene is there and substituted by 6 different substances. In addition, by porphyrin ring, it's attached by the pi stacking to the center. Line notation. In the field of the chemoinformatics, line notation are very important, and in the even people also consider IPC name as a line notation, but because of their very big nature and several hyphen commas, they are not in the tradition. We will see only few. This was one of the early line notation where people wanted it. They used some alphabets out of the 26 to describe different chemical structures. You can see, and we will get such names for those molecules. But problem with this that we cannot describe using only those 26 alphabets all the structures, and one molecule can have the multiple WRN. Crossdale was another where we give the numbers to the molecules. And we usually don't give the name of the carbon, but rest we define after the number of. So this way we can also define the molecule in the computers, and this is quite fast compared to the previous one. This is the smiles. That is one of the most popular and still used heavily in the computational chemistry field. So there are mainly 5 types of the attributes in the smiles: atom representation, bond representation, representation of the disconnected structure. So here we directly use the chemical symbol present in the periodic table. If it is ionic, we put in the square bracket, and different type of the bonds by single bond, double bond, triple bond, and the aromatic bond. Right? For methane, we can have simple representation on the carbon. It will save your space in the computer. If your supervisor asks send me the 100 structure of molecule what is inside, you can easily copy paste the smiles. You can send to your boss. And so this smiles is different from this smile. In addition, if there is a branching in your molecule, like here, we can consider for carbon offering the branch or hydroxyl branch, or this is a branch. So we can put the branch in the parentheses. And if we have a ring, we can convert those ring system by cutting any bond to a linear chain, and we can easily make a smiles. So whenever you cut the bond, we provide some numbers, so we can know where we have cut off those different atoms. So no matter how complex is the ring, like if you see this cubane, just be cutting the bonds, we have converted this complex to very linear structure, and you can easily write the smiles from them. So problem with that smiles is that one molecule can have the multiple smiles. And one your colleague is collecting some molecule like particular target from a reference articles, another from review, and here maybe several duplicates you don't know. So how you will sort out, because one molecule can have the multiple smiles. He may be using Camdron, another may be using Biomet branch, different software. So in order to solve that problem, to have a single smile for a single molecule, concept of the canonical smiles was given. There are algorithm by which no matter what is the molecule, it will always give you single smiles. And that is the canonical smiles. So that's why we can have for that 1-to-1 relation. So this way you can easily deduplicate your data set, no matter what purpose you are using for QSR development or machine learning purpose. In addition to that, in the literature, you will see different flavors of the smiles. Chemical I have described, but in addition, there are several others: arbitrary, isomeric, unique, absolute, generic, and from software to software vendor to vendor, we will have different softwares, their algorithm, they will generate different type of the terminology. So you have to be careful what software you are using, because some of them may not have the stereochemistry information, isotopic information. So as a medicinal chemist, your molecules should be perfect, should not have any problem. Recently, because whatever the smiles were, it was developed by Daylight company. But if you are interested to give some new attributes, new information, we found the smiles. So for that purpose, so all the people can openly contribute the smiles. So that new concept of open smiles is given. so that anyone can contribute. And it is quite similar to Placer. It has got additional attribute for definition different any type of the stereochemistry and bond types. Like coordination bond is not there in the traditional instruments. We cannot represent the radical atom. So this was another civil line notation, and where we have explicitly mentioned the hydrogen, and more or less other features are similar to the Ismails. In 2001, in Chile, there was a trust. They were interested, can we develop some unique identifier for chemicals, like every Indian has got an Aadhaar card, right? So that no matter what molecule you synthesizing, what molecule European synthesizing, if you use same molecule, should know what are those molecules. So to solve that problem, there was group of the person in the NIST in USA, and I met the chairman of this who constituted this INCHI, Heller. So he thought that we should start something new, identify so that it can identify any chemical molecule. So they given this concept, International Chemical Identifier, that we look at INCHI. So it has got a layered structure, and it has got a different type of the information about molecular formula, what are the connectivity between the atoms, hydrogen information, charge related, isotope related information, and stereochemical information. Now you tell me what information is missing. Everything is there. So by using that, you can easily search any compound in the Google. You can store and you can deduplicate the molecules, because each molecule will have a unique INCHI identifier. Problem with this INCHI identifier, why? As the size of molecule increases, length of this INCHI also increases. Molecule is very big, as we have seen. It may come to full page. It may extend to the next page. So it was very difficult to enter the INCHI, though it was very good solution to the chemical community. So they started some hash version of the INCHI. There is only 27 character hash code. They call it INCHI key. No matter how big is the molecule, you will always get the 27 character. So this first red portion, this denotes the main layer related to the chemical formula and connectivity. Rest part will incorporate information related to stereochemistry, isotope, and last two characters, these indicate the version, like S indicate this is the standard INCHI. A is the represent the version A, and O denote the whether molecule is neutral or protonated. So because at that time they designed this INCHI or INCHI key, they tried to incorporate some information about tautomers. But recently, we studied that INCHI is not very good to handling the tautomers. So we analyzed it using 9 chemical databases. We found that only 30% cases it is able to identify its own tautomers. Not, and it is failure in the case of 70% of the structures. So it is very good, and that's why now INCHI want to revise the INCHI. They want to come up with new INCHI with more powerful features. So it can identify all type of the tautomers, all type of stereochemical problems, all type of the organometallic compounds. So that version will come in 1 or 2 years. It is under the development phase. So beyond the SMILES, so we can draw the structures within the SMILES. But if you want to search some structure, some functional group, some scaffold, for that there is a language using the SMILES. Here we have some of these languages there. We have the logics also for each atom and bond. Using that, you can build any type of the query and you can search easily. So I will give some examples so you will understand it very easily. Suppose you have the 4 compounds like phenol, aniline, thiophenol, and the bromophenol. Those all compounds can be represented by simple single structure. All those different substituents are here represented by using the logic. Over here, it may be oxygen, it may be nitrogen, it may be sulfur, it may be bromine. The rest is the cyclic structure. You can count these are 6 elements. So this way, this is very powerful. You can search in the PubChem in any database. Okay, I'm interested in the Michael receptors. You write the smarts for the Michael receptor, you will get the only molecule which has got a Michael receptor. This is the main beauty of this smart language. So I will try to finish because constraint is there for the lunch. Similarly, there is one more language, ISMIX. This is the language to automatically modify any molecule, to create any molecule, to write any reaction. So very simple example over here I have given. So this is a representation of how to write this mix. So here you have the reactants, here you have the product, and the double arrow greater than indicate that this is the one side, this is another side. So this way you can write any chemical transformation. So it is very easy. Suppose if your boss is asked, okay, draw the reaction between the ester and the any primary, secondary, you will draw the structures. If your boss will give you 1000 structures, how will you draw? If you know the mix, within 1 minute you can write and draw the 1000 structure very easily. So using that, we have developed one tantomerizer using those different 80 rules based on the SMICS and the smarts. Chemical reactions. So in addition to the reactant product, all other information, catalyst, solvent, other things, you can define in between over here. If you don't know that information, just you put those two double greater than symbols. Okay, so you may have the several reactions, but we don't know how to identify, how to differentiate between similar, dissimilar reactions. So recently, this concept of Rinchi is going on. Rinchi means Inchi for the reaction. So this way, here are different layers which will have the information for reactants and product and the catalyst and solvents others. So you can easily differentiate or aggregate different type of the reactions. If you have the mixers, of course, medicinal chemists are sometimes getting the mixers, RNAs, diastomers, mesomers, and the people may have the different physical mixers. How to differentiate between, if you know the concentration. So for that, Minchi is also started the Minchi. So Minchi means Minchi for the mixers. So this way, so it will have information about the formula, connectivity, and other stuff as traditionally, but percentage, polar percentage, and other any kind of the concentration you can define here. So you will know, okay, this mixture is different from that one, and the numbers can be defined. Okay, this is the main caffeine, only N1. Here are two components. You will define 1 and 2. So you know how many chemicals are there in that particular mixture. So open source tools, there are several open source tools are there for the chemoinformatics work. Like this is one of the most popular RD kit based on the Python. Wrapper is available, though it is written the C++. Open Bible, I hope some of maybe already need to convert one file format to another file format. CDK, it is based on the Java library. And this is the Perl based Maya Chem tools. There are several small libraries are there written by some Indian scientists. So you can just use them for your any kind of the work. And this is the data warrior. This is the one software you can easily do so many kind of things by clicking the button rather than programming coding. But what I told, if you know a little bit Python, you can make those, I said 1000 compounds in one click. Just to give the input, okay, this is my primary or secondary amine collection, this is the ester. Write a 3-4 line code, you will get all the structure. As I already mentioned in the morning, you learn Python, Python is easier, several libraries are available. And these are some of the commercial toolkits like OpenEye. I have used this toolkit chemistry that is written in the tool command language. That is very quite powerful, but you won't get any blogs and tutorials. This was written by only one man. He do not have any other employee in his company. He wrote this program in his postdoc, and now he's converted that to his one company. So with this, I will end this presentation. I hope you may be introduce yourself about different topics and software related to this field.
Thank you, Dr. Dhakar.
If you have any query, please you may contact me anytime or through computer.
Yeah, we'll share his number. You can also directly contact him. And we appreciate his.
Dr. Devendra, I have a question.
Yes.
Now, I am a senior citizen. What language should I learn?
Python.
Python? Not Inchi and Rinchi and Minchi?
No, all those codes are freely available at the Inchi Trust website. So in next version, all will be incorporated one tool.
So for old people, Python is the best.
Yeah, for everyone it is very easy. Everyone within 1 month, I think you can write very small code for any stuff.
And I will advise go for ChatGPT. Yeah.
Many of them are already aware.
Even the people like me who are very ignorant, sometimes I ask the GPT to write the code for me actually. Why is it to waste my time? I can ask if it's making a mistake, just ask him the correction actually. Have you used the ChatGPT? Yes. Try ChatGPT. Yes. In Python, it's like very well coding. And now with BioGPT is also. Yeah. So they are very nice software.
Thank you.
Quick question. If I have a molecular formula using cheminformatics tools, can I enumerate all the possible structures, constitutional isomers, that molecular formula?
Yeah, of course, can be explored, but I can check whether that option is available. But I suppose it may be available in article. I will check it.
Yeah, please. I will be in touch for some tool where I have a molecular formula. I enumerate the constitutional.
That is very good. But I think got a chance to explore that. The only molecule from part of the but one day there is one database developed by the Redberg somewhere in Germany, where you will only at 6-7 elements, basic elements of the chemistry. By permutation combination of those different 7 elements, we can enter more than billions of the chemicals. Just to okay, I want the molecule, I got only 3 elements. I want the molecule 6 elements. 10 billions. GDP database is I think.
So please join me in thanking him once again. We can continue the discussion over the. Revin, are you there?
Yes, I'm here.
Wonderful. Nice talking to you after so long.
Same here.
We are waiting for a few more participants to come in. We had a lunch break here.
Great.
So they are just beginning to assemble.
Oh, fantastic.
We already have Professor Ragha, Professor Kutino with us, the audience. You might know them already.
Yeah. Hello. Nice to meet you. Can just see if my slides show up.
Yeah, you can share that already.
Let me know if this works.
Yeah, we can see that. So maybe we'll wait for just another minute and then.
Sure.
You can start.
Mm-hmm.
Pick you up this early.
Yeah. Well, I normally wake up around 4, so today it was just 3 o'clock, so not too bad. Yeah.
So how is your family?
All good, all good. Yeah, I guess getting through the winter.
COVID is all behind us there also.
Pretty much, yeah. There's not much. There's people who still take a lot of precautions when they have reasons, but mostly it's gone. But the one downside is that when kids wear masks for 2 years and then they don't wear masks for a long time, they get sick very often.
their immune system didn't get enough training.
Yes.
So I believe we can start whenever you are ready.
Great. All right. I'll get started. Good afternoon, everyone, and thanks for the opportunity to present. It's always great to kind of come back and share things that we've been working on here at Pfizer. And hopefully I can give you a flavor of what chemical biology as a discipline does in industry. Um, it is a field of science that works very much at the intersection of chemistry and biology, as the name would suggest. And when I gave this talk last year, I had a slightly different flavor of it, and today I would like to present things around the DUB family of proteins. So this is the deubiquitinase family of proteins, and wanted to make it a little more specific in terms of things that we do. Uh, there's challenges that I would like computational chemistry and the AI community to sort of take up and help understand this gene family a little bit more as well. And just as a bit of background around myself, I've been with Pfizer 7 years. Um, I was at NIPER Mohali from 2004 to 2006, and I had the pleasure of working with Professor Rahul Jain there um, alongside Vaibhav. And since then, my basic training in during my PhD and postdoc was medicinal chemistry, molecular pharmacology, and then learning a lot around chemical proteomics, which is something that we have used to sort of bring around this story. So I'll touch a little bit around chemical biology and what that is, and it can take many different flavors. Hopefully my slides advance here. Okay. So in terms of a discipline in drug discovery, chemical biology is a relatively new discipline. And traditionally, for several years, either pharma has relied on phenotypic screening to find molecules or doing binding assays in isolated in vitro systems such as this. So you take a protein or kinase of interest and you screen a large collection of molecules, either through an enzymatic assay or through SPR and technologies that are coming online. But when you screen in an isolated system, it is not the same as screening in a cell, which is essentially a very complex machinery of chemical reactions ongoing simultaneously. At least that's the lens through which I try to take a look at the cell, which manifests into biology. But what I really want you to take home from this slide is that when you screen in an isolated system, and usually it translates, but sometimes it doesn't, but it's really not equal to screening in cells. And that is something that, at least in industry, there's been a big push over the past few years to try and screen more and more in cells. And I'll come along reasons as to why. So we want to understand what our compounds do in living systems, potentially in vivo, but that's harder to do. And but at least in terms of doing experiments in cells, we are enabled through advances in bioorthogonal chemistry, something for which the Nobel Prize was awarded in 2022 for click chemistry, advances in proteomics, functional genomics, and now I would even say machine learning are fueling this revolution on our end in terms of chemical biology. So where is chemical biology in the drug discovery process? You could think of drug discovery in this very simplified diagram here. You start from target identification and going all the way to clinical work. We have worked definitely at the target identification stage, and we've also worked in the clinical space for specific projects and specific problems. But majority of our work comes in this screening and design and lead development phase, where we are trying to understand molecules. What do they do in cells? How do they engage with the target? What are the selectivities of these compounds? And that's really what kind of put us on the map. So that's what chemical biology is in terms of the drug discovery. I'd like to think it's sort of squarely sits in the middle. There's other things that we try to do. There are proteins that you cannot really drug easily. I call them yet to be drugged proteins. There's folks who like to call them undruggable proteins. But essentially things like transcription factors or intrinsically disordered proteins, can you start drugging them? And there's ways to start thinking about those, but maybe someday in the future I'll talk about that someday. But really what has driven a lot of the acceleration has come from advances in chemical probes that have helped us understand our molecules better. And today specifically I'll talk about the advances in chemical probes and related to a specific gene family called the D-ubiquitinases. And I might refer to them as DUBs every now and then, so pardon me for that. And I'll talk about D-ubiquitinase activity-based probes that we've been working on and how they are getting implemented in the pharmaceutical industry, at least at Pfizer. So D-ubiquitinases are part of this whole protein homeostasis machinery in cells. Now your purple blob here is a protein. A protein gets synthesized. Every protein has its own half-life. So you can imagine a protein getting synthesized, the gene transcription occurring, the pre-mRNA forming goes to the mRNA that gets translated into a protein. It eventually undergoes a bunch of post-translational modifications, localizes where it needs to localize, does its job. And then at some point, the protein has to be recycled. It has a natural half-life. At that point, you have this modification, which is 8.4 kilodalton modification, about 76 amino acids of a protein called ubiquitin gets appended on the protein. So let's start here at the bottom. So you can have multiple types of ubiquitinations occurring on the proteins. These normally occur at the epsilon lysine on one of the surface lysines of this protein. And different types of ubiquitinations can signal for different events in the cell. You can have a K48 type ubiquitination, and also the K11. These target the protein for proteasomal degradation. There are some linear N-terminal ubiquitinations that I don't think we understand fully. They can result in kinase activation. And then there are these mono and diubiquitination events that occur in the cell that can result in a plethora of biological implications. The way these ubiquitin groups get put on proteins is that in your cells and in human cells, you have two E1 enzymes. Their job is really to convert ATP into AMP and create this activated E1 complex, which then gets transferred to an E2 protein. There's about 40 of these, 40 genes that encode for E2 proteins in the cell. And then this activated thioester complex essentially gets transferred onto an E3 protein. And there's several E3s in the human body. These are cell type specific, but there's about 530 of those. They can be broadly classified into the het E3s or the ring finger E3s. And really the difference here is that this goes through a covalent mechanism, whereas the ring fingers just have a binding element. There is no covalency to it, and that's how you start putting on different ubiquitin groups on the proteins, and they can signal for different things. But then you come to these D-ubiquitinases, and as the name suggests, they clip off the ubiquitin from these already ubiquitinated proteins, and the ubiquitin, there's a finite pool of ubiquitin in the body, so it kind of just keeps getting recycled, and it's a delicate machinery. It's a delicate balance, but D-ubiquitinases will clip off the ubiquitin and either protect the protein from degradation, increase its levels, or also prevent some of these downstream activation and functional events. So that's sort of just a brief overview of the protein homeostasis machinery. I can try and advance my slide. So D-ubiquitinases in general work through a thioester, a thiol hydrolysis mechanism where the protein gets presented with the ubiquitin chain. There's an activation of the thiol. You form the traditional oxyanion hole, and eventually the ubiquitin gets clipped off, and the ubiquitin is now appended onto your D-ubiquitinase. So there's a step in this process, which then eventually just gets hydrolyzed through a water molecule to regenerate your deubiquitinase, and also the ubiquitin molecule itself gets regenerated and goes back in the ubiquitin pool for further recycling. So this is sort of the mechanism through which these enzymes work. Most of them work. There's some that are zinc dependent, which I'm not showing here. And in general, a deubiquitinase has a finger, palm, and a thumb-like structure, as shown here, representative with USP7. This is sort of the catalytic site near the thumb region, where you have the catalytic triad, the aspartate, the histidine, and the thiol here. And this was co-crystallized using a ubiquitin aldehyde because you had to kind of make sure you form that covalent atom. So this was a structure that was published a while ago. But this is sort of generally what the deubiquitinases look like. There's subtle differences. There are large conformational changes when ubiquitin binds as well. And we would like to understand this gene family a bit better because we think there's a lot of opportunity to drug this protein, these types of proteins. The DUB subfamilies come in various flavors. This is just a representation. You have the USP family, which these are about 100 proteins, and the USP family is roughly about 60. You have the ubiquitin carboxyhydrolases, which from the UCH family, the otulins, the Mindy family, the Josephine family here as well in the green. So you have several of these proteins. The JAM families are the zinc proteases, which we really don't understand fully. Some of them are part of the proteasome as well. So given this diversity in the gene family, most of these work through cysteine protease hydrolysis mechanisms. And we would like to come up with 1 or 2 or 3 small molecules that can react and bind to all or as many of these as possible. Why do we want to do that? In order to make a small molecule drug that specifically inhibits only one of these, we need to be able to understand that when we put that molecule in cells, how many of these deubiquitinases or other thiol-containing enzymes do our small molecules react with or bind to. And in order to that, we need some specific probes. These types of probes are called activity-based probes. And how can an activity-based probe enable inhibitor discovery? So that leads me to my next slide here. You have a protein, so what do you need to generate activity-based probes? You generally need a protein that has a binding site that can be exploited. We feel that the deubiquitinases clearly meet this criteria. Covalent probes are pretty great for doing downstream proteomics analysis because you can do click chemistry and you can do pull downs using streptavidin resin and then query either by Western blot or mass spectrometry for downstream readouts. So you have a protein that has a binding site. We know that this has some inherent chemical reactivity, some intrinsic properties, and deubiquitinases fulfill that criteria with a cysteine in that position. It is a fairly reactive nucleophilic amino acid. Can we come up with warheads that are complementary to the reactivity of this residue so that you can result in the covalent modification of this protein? You need some sort of a binding component, a molecular framework that essentially gives you some sort of selectivity towards your protein or proteins of interest in this case. And then you need some sort of a reporter, so you can conjugate. You can put in an alkyne handle, and you can end up doing click chemistry to then do some sort of pull down and read out experiment. So that's what your activity-based probe looks like. What was the reason why we want to also investigate these types of cell permeable probes is that there were some DUB probes, and so 2 reasons. One, this is precedented, so activity-based probes have been developed for entire gene families, such as serine hydrolases. They've been used in pharma and in research for over 20 years. They contain fluorophosphonates, which will react with low pKa serines. So those have been developed. Activity-based probes for kinases have been developed. activity-based probes for protein, arginine, deaminases have been developed. So you can do this for a gene family. This has been done before. And deubiquitinases are indeed a class of proteins that we feel are ripe for this type of work. There are definitely probes that don't enter cells, so they're not cell permeable, and they have their limitations, which is why we wanted to invest in developing probes that we can put on cells and maybe even put them into living animals and then look at target engagement, selectivity, and things like that in vivo and in cells. So this was the activity-based probe. So why develop cell-permeable pan-dub or relatively promiscuous compounds that help us understand what these dubs do? So this is again a different representation of the dub family. There are activity-based probe approaches. All the way up until now, they were all cell lysate-based. They are just bigger molecules. There's some fantastic work being done at Oxford, where Benedict Kessler and his group have developed these and indeed used them, and they're useful. It's just that the limitation is you cannot use them in cells. And the reason being, what I'm showing here is a Western blot of a proteasome inhibitor probe. Here, this is a vinyl sulfone that ends up reacting with a proteasome where you can look at things. But you can clearly see that when you're using things in lysate, so this is the same cell type, the EL4s. This is a Western blot. You're looking at some of these proteasome subunits. You can see that in the lysate, when you add this probe, it reacts with the B1I subunit fairly well. But then when you put that in cells, it suggests that the B1I subunit, the beta-1I subunit, is actually indeed inactive in the cell. So you're likely to get false readouts from a lysate-based experiment. And also your labeling for the B5 is enhanced in cells, suggesting that this is the beta-5 subunit is actually the more active one in the cell. So the folks who've developed these probes also say that they've observed substantial differences between cells and lysates, and which is why we want to be in cells. We want to be in a small molecule milieu and try and understand these compounds better. So what could you do with a cell permeable deubiquitinase activity-based probe? Well, you could screen several compounds. So imagine you have a small molecule that will react at that catalytic site with multiple dubs, and you can do selectivity profiling of compounds. Why is this important, you may say? The reason is that with small molecules, you do want to figure out what their off-target and selectivity profiles are. There was a dub inhibitor put into the clinic for multiple myeloma, VLX 1471, I believe it was. And it was an acrylamide small molecule. It was progressing, but unfortunately it did cause a death in a clinical trial. And some of those, while the exact reasons for that are unknown, the molecule was definitely not selective across the whole gene family and may have had off-target effects that we would like to read out. So those are the types of things that you can address on a screening campaign. You can do screening in cells, figure out how many dubs does my molecule react to it, and the red here just shows that there's more reactivity. These are somewhat selective compounds, but there's others which are not selective, which I'll show in a few minutes. You can do occupancies, and by occupancies I mean what is the concentration of the small molecule that you need to put in a cell to achieve 50% binding. The reason this is important is that you can derive effective concentrations to get to a therapeutic index when you run your trials, and you set doses for clinical candidates. So I think that these types of data are critical to understand what is the dose that'll be effective for pharmacological activity. You can determine degradation and resynthesis rates of your protein with these types of probes. And again, these are all data that we've generated using different types of probes. And the really cool thing that I thought was very interesting, this was data. Unfortunately, I cannot share the identities of these genes, but we had a hypothesis that if you provide a stimulation, certain dubs or only one dub would actually increase in its activity in a cell. And this was exactly what we found. all dubs had no change in their activity, but using the probes, we were able to show that under a certain type of stimulation, only one deubiquitinase gets activated. So again, this can validate your therapeutic hypothesis and validate targets early on in a drug discovery program. So these are the types of things that these probes can enable. And this brings us to where we started. So we started back in 2016. So this is still work. We're still trying to wrap up this publication, but 2016 is when Professor Ed Tate at Imperial College published this chloroacetamide, this methylpyrrole containing chloroacetamide, where, chloromethyl ketone. And he showed that when you do proteomic analysis in a live cell, this compound can engage 12 dubs. That was a good start. 12 out of 100 is not great, but a chloromethyl ketone, small molecule, can get into cells, fulfill some of these criteria. So we ended up collaborating with him. Started the collaboration in 2018, 2019 timeframe. And our strategy at the time was to take his scaffold. There's no real structural understanding of why a methylpyrrole containing a benzyl group at the west side of the molecule really is active. But we decided instead of changing the Ki component of this molecule, we thought we'd go ahead and do a warhead scan and see what kind of warheads will help us expand our coverage of dubs. Can we go from 12 to 20 to 30 and more? The challenge becomes what cells do you work with? And not every cell expresses every dub. We wanted to be as comprehensive as possible, so we developed a greedy algorithm that looked at RNA-seq and proteomics data across 100 cell lines, and we kept asking the question, how many dubs can this cover? So again, there was a bioinformatics element to this, and it was an iterative algorithm. Liang Zhu, who created the algorithm, calls it the greedy algorithm. And we came up with 3 cell types, the U2OS, U87MGs, and T47Ds. And then these are together, they give us the best coverage, about 75 dubs. If we wanted to add 5 more, we would have to add 5 more cell lines. So that would have expanded the scope of the work significantly. So we decided to stay with 3 dubs. What our initial profiling suggested was that the cyanamide or the cyanopyrrolidine warhead is the most promising. And this was occurring at a time when compounds were getting into trials. Mission Therapeutics and Forma Therapeutics, 2 companies, were definitely leading this effort, and they were finding cyanamides or cyanopyrrolidines as promising as well. So it was good to kind of see some of our data reproducing what was generally known in the field at the time. So the blue one here, the CMK, the chloromethyl ketone, is the original probe published in 2016, and this was the cyanamide functionality that we found. We tested a bunch of others, and really we put these in 3 cell types and asked the question through proteomics, what dubs are engaged? What warhead is the best? And really what you want to see here in this figure is that on the left are all the deubiquitinases that we were able to quantify in these cell types. What you want to see is a broad swath of light colors across a column. So while there are certain probes that did engage dubs in a differential manner, the broad stripe was only observed with the cyanamide or the cyanopyrrolidine probe. And that looked most promising from these early experiments where we were able to pick these up. So the cyanamide probe, we characterized it further. We figured that this was non-toxic and also shows in vitro pan-dub inhibition. So we took these probes and put them through a biochemical screen because we tested them in cells because that's what we want to be, but we also wanted to see if there's biochemical inhibition. And indeed, you see here that the cyanamide is the probe that inhibits most dubs, at least in the panel of 40 or so that were tested. Some of these other probes were cytotoxic, so the chloromethyl ketone is indeed cytotoxic at about 10 micromole or even lower concentrations, depending on the cell type. But the cyanamide is really non-toxic. So the chloromethyl ketone is a toxic probe, kills the cells. That's not what we want. We want a cyanamide, or at least something that does not kill the cells. And this was pretty flat lined up to higher concentrations, which was very good to see. The next question we wanted to ask through a proteomics experiment is there any enrichment of dubs over background, because these are reactive molecules. They will go in and react with several proteins that do contain thiols. So this is sort of a log 2-fold change over DMSO graph that we are showing, and this is just the name of the probe that our collaborators at Imperial College gave. In your gray or black is just all protein, so that's sort of their median intensity normalized to 0. And now we're asking the question, is the blue line higher than the gray line? The red is essentially all hydrolases, so several other hydrolases were included. I'd have to go back and check which ones these were, but essentially at about 12 micromolar in cells, you sort of get the highest difference. As you keep adding more and more compound, you're likely to react more, and this difference is likely to get muted a little bit. But again, it does quantitatively enrich dubs over other proteins. You're never going to get a night and day, but as long as there's an enrichment, that was good enough for us to go ahead. We tested these probes in cells using known methods and the method that we developed, and the take-home message here is that our probes in the experiments that we used were on par, or at least slightly better than the current state of the art in the field, which was the lysate-based probe. So we do enrich several dubs. We didn't show all of them here. This is just a representation here. So overall, we're picking up dubs, enriching them. So if you notice, I did not touch on this carefully, but this probe is a mixture of enantiomers. And we were intrigued to figure out if one of the enantiomers is better than the other, and if we can separate these out. Well, it turns out that both these enantiomers are generally equipotent. There are subtle differences. So for example, UCHL3 in this case has a preference for one of the enantiomers. We didn't know which one was R or S at the time. We just separated them. But it has a slightly higher preference for probe 12A, which is one of the enantiomers. Sorry, the blue one here, not the green one, the blue one here. So there's slight preference. It reacts a bit more. UCHL5, for example, has a preference for probe B. So you start getting higher labeling early on with one of the other enantiomers. And for certain other dubs, there was no preference. So for example, USP10, there was no bias between the enantiomers. So we felt that at least the presentation of the cyanamide in that active site during that oxyanion hole sort of state, there was no difference, but there are definitely compounds that show stereochemical preference for the newer probes that we are developing. This is something that we put into bioRxiv, and we're working on wrapping this publication up. So this is what was most interesting. Can we actually use it to profile inhibitors for dubs, which was exactly what we developed these probes for. So this is sort of the general layout of the experiments that we did. You go in to cells with a known inhibitor that you've developed. You let the cells incubate with these compounds for about an hour, and then you go in with your probe. So the beige or orangish brown color here is the probe. This has the alkyne handle, and the hypothesis here is that for a dub that did not react with your original blue molecule, your probe can go in and bind. But if the active site is already occupied with a small molecule, there is no possibility for your probe to go in and bind. And then you can do your click chemistry, streptavidin engagement, enrichment, and then read out by mass spec or read out by Western blots in this case. And here we're showing that this is a USP30 selective inhibitor. So again, it's a cyanamide, this Pharma Therapeutics molecule FT385. It has an IC50 of about 1.5 nanomolar, at least in the biochemical, and we tested them in T47D cells. And you can show that as you increase the amount of the USP30 inhibitor, and when you chase with the probe, in this case, you should start seeing less and less of USP30 because the active site is already engaged. And we clearly see that at 2 nanomolar in cells. So is the IC50 1.5 nanomolar? Most likely it is. It's a pretty good molecule. You can also do this with the UCHL1 inhibitor. This is a very interesting pair because you have an active compound, compound 15, and then you have an inactive inhibitor. So the only change here is the stereochemistry of the cyanamide. So here again, you want to see discrimination, and you see that indeed when probe 15 is added, you see competition. And when you go in with the inactive compound, so there is essentially no blue molecule here, it's all inactive. And when you go in with the probe reacts, you pull down UCHL1. So now you know that target engagement is occurring at the active site. We have other data to suggest that as well. So it helps us profile these compounds in cells. And what is interesting here is that perhaps this molecule that has a biochemical IC50 of 90 nanomolar might actually be more potent in cells. Because if you look at 50 nanomolar, you've lost half the signal, or more than half the signal in this case. So your occupancy is actually better than what you measured biochemically. So imagine if you just go off of biochemical studies and you set effective concentrations that way, you'd probably dose more than what you would need. So again, those are the things that we would like to discern from these types of probes. You can understand basic biology. I won't go into all these details here, but essentially MYC is an oncogene, can result in tumorigenesis. We wanted to see if we developed a model system where we have physiological MYC or deregulated MYC and ask the question, are any DUBs more or less expressed when you have deregulated MYC? So this cell system, you can go from high MYC to low MYC just by adding doxycycline and estradiol by regulating the gene expression. And we went in with the probe, and we also said, do we see changes in the global level or just the activity of these probes? And this is just showing that you can go from a high MYC to a low MYC expression here by the Western blot. Here, what you're looking at is on the x-axis, you have the low MYC on the left, high MYC on the right, and then this is your activity of the DUB. And here you have just the abundance of these proteins. So you want to see things move on the x-axis without moving on the y-axis. So some things just change in abundance, whereas things like UCHL3, USP7 to an extent, USP47, all of these are down-regulated in their activity relative in the low MYC conditions. So are you losing activity as higher and higher MYC is getting expressed? And can that help us understand some of these tumors? So that's, again, basic biology target ID that you can do using these types of probes. So using the cyanamide probe, we were able to at least capture about 35% of the dubome. These compounds are non-toxic. We can use them because they're active site directed, apply them to study DUB inhibitor profiling in live cells and also understand some basic biology using these probes. Dahe in my group, so all of the work on the left was done with our collaborators. When we took the probe, we put them on slightly better mass specs. We actually find that these compounds pick up about 50 plus DUBs. And if you do the experiment really carefully, you can get up to 60 DUBs with these compounds. Which is incredible. These are the things that we've done with these compounds internally. So again, this was something that I showed where we were able to show a certain stimulation only upregulates one of the DUBs, not the others. And this is the kind of data that gets me most excited, is inhibitor profiling for cellular selectivity. So when we had a DUB program internally where we were looking at inhibitor selectivity profiling, these early compounds were fairly promiscuous. So if you look at these reds, you're seeing that at 10 micromolar, and I'm just showing a snapshot here, that several DUBs were getting engaged by these compounds, or even as low as 600 nanomolar, you're getting dose-dependent engagement of several DUBs. These data were used to understand how to design away from these off targets, and then some of the later molecules in the program showed better selectivity against some of these targets, and these are all deubiquitinases. So again, you're using cellular target engagement to inform design that can give us better, more selective molecules that we can then put into animal and human systems. The question often gets asked is that are cyanamides and DUBs made for each other? Is this a warhead that constantly gets picked up by multiple pharma companies, and are they made for each other? And the answer is it's complicated. It's not very simple. Dubs prefer cyanamides. It looks like that the active site sits in a tunnel where the cyanamide actually kind of makes those interactions and can get into that. But cyanamides don't always prefer dubs, so the love doesn't go both ways. There are definitely non-dub off targets, as you can imagine. This is still a reactive warhead. The Ki component has a big role to play, and we're still trying to understand what is it about the dub active site that lends itself to these cyanamides. There are things that are thiol proteases like biotinidase or omega amidases and aldehyde dehydrogenases. They get engaged with these molecules. In fact, some of these are more potent than the dub itself. You can imagine some molecules will react with capepsins or cysteine-containing proteins like PARC7. There's some very hot cysteines on those proteins as well. So it's not a relationship that is made for each other, but what have we learned so far? We learned that pan-dub cell permeable probes can enable study of these inhibitors in cell systems. We can figure out selectivity, occupancy, differential deubiquitinase regulation, and even non-dub targets of cyanamides. The thing is that all of this is done by mass spec, and each experiment is at least a week long, if not more. It's a low throughput assay. We need to make it higher, faster, better. Can we do this faster? Can we still be in cells? And for that, we've reverted to this type of system called a nanobread assay. It's a fluorescence transfer-based methodology. Excuse me. What you do here is you take your protein of interest and you tag it with this nanoluke, a sort of fluorescent or bioluminescent handle. And it's non-fluorescent, or it doesn't give a signal on its own. But when you have a small molecule that has the corresponding fluorophore appended to it, that's when the two come in contact and give off a breath signal there. But if your active site is now occupied with a small molecule, there is no transfer, there's no tracer transfer energy happening, and then you no longer get signal. So essentially, it's like a mass spec readout, except in cells, and now you're looking at fluorescence instead of peptides. Promega is a company that has advanced this platform extremely well. They have kinase assays using nanobread. They've essentially populated pretty much a large chunk of the kinase tree here. But can we take some of these probes and convert them to nanobread and essentially make nanobread probes for dubs for live cell target engagement? So Kari in my group and Nathaniel worked together to kind of figure out how do we do this. And again, this shows that for one of the dubs, you get fairly good competition. Some of these compounds are pretty potent. And when you mutate the cysteine to a serine, where you should not get any signal, if these compounds are specific, you should see a flat line, and that is exactly what you see. So this was great to see. We can convert these mass spec assays into nanobread assays. And again, this is a different competitor that we tried, a different compound, and this is extremely potent, I'd say single-digit nanomolar compound here, or potentially lower in cells. So these are the kind of things that we can do with these probes. We had an external collaboration that helped us. We were able to get through some of these, but these are still not potent enough. We still don't like the probes that we have. We think we can do better. You would like to use them at single-digit micromolar, and we are still lacking structural insight. So while not all dubs have been crystallized, and when we were starting this work, AlphaFold was just sort of coming along. We are still trying to understand the structural determinants of these compounds and the cyanamides in general. Can we do a bit better? What are the lessons that we've learned? So we did a whole lot of work around serine hydrolases back in the day, and we were able to do in vivo target engagement as well. But really the kicker here was that I touched on fluorophosphonates a little bit early, but when we were able to use a mixture of probes for these types of a mixture of probes for serine hydrolases, we were able to increase our coverage and use it at a much lower concentration. So can we apply some of those lessons that we learned with serine hydrolases into dubs? One is a serine-mediated hydrolysis, the other one is a cysteine-mediated one. We should be able to do that. And the reason we want to do that is, sorry, I'll just run through this one. So for serine hydrolase probes, we were able to take, if you just take a single probe, you enrich about 90 odd serine hydrolases. When you take the probe mix, you enrich about 100. You get much better signal per serine hydrolase, and you can calculate occupancies for some off targets as well. So some that you were not able to engage previously. So can we do that for tubs as well? And so for that, we sort of went back to some biochemical data. We had 1,000 compounds that we had filed for tubs. We picked the 5 most promiscuous and potent ones. We converted them into newer probes, and we're testing them right now in cells. The data just came out 2 weeks ago. Can we start using pools of probes to try and understand and get better coverage? So our goal for deubiquitinases is a set of probes to study all 100, if possible. I think we're halfway there. We might be about 70% of the way there. We are using them in vivo and ex vivo target engagement experiments, and also use modular approaches to allow some higher throughput platforms like NanoBread. And hopefully someday I can come and talk about those types of probes as well, and things that we are doing much more with this gene family. With that brings me to my last slide. Wouldn't be complete without our acknowledgements to our collaborators, Professor Ed Tate at Imperial College, Dan Canoli and Fang Yuan, who did all the work for the collaboration, 2 great postdocs. And then folks like Chris, who make probes available pretty quickly, and then guidance from Daph and Monica, and then for Tahe, Nathaniel, Kari, Liang, and Sheila for a bunch of work, and other colleagues as well. So with that, I'll take any questions that you guys may have. So happy to answer any questions.
Yes, it is open for questions. Anyone from the audience? Okay, I guess none. So thank you, Jamin, very much for your wonderful lecture and taking us from the basic to the translational aspects of the drug discovery. So we very much appreciate your time spending with us. As a token of appreciation, we would like to show you and then post you our token of appreciation. I request Professor Raghava to in silico hand it over to you.
Thank you.
We have done this 2-3 times in the workshop.
No, thank you. I see it. Thank you so much. It's a pleasure and honor to be invited. So thank you so much for that. I appreciate that. And hopefully someday I can give you more details on things. This was what legal had approved for me to talk.
Yes, please do. Whenever you are in India, let us know. We'll like to have you here in person.
Definitely. Great.
Okay, thank you so much.
Yeah, thank you.
So now we close this session and we will gather at 4:30 for the valedictory function.
Hope all the participants are enjoyed thoroughly all the sessions from yesterday till today, including the hands-on sessions happened even just 2 minutes back. So, and you got all the insights from the eminent speakers who are available both physically and virtually. And to proceed with the valedictory session, now I'd like to request the guests to come on the dais. Registrar Dr. Radhakrishnanan, Associate Dean Dr. Sanjay Banerjee, Professor GPS Raghava from IIT Delhi, Professor Evan from Bombay Medical College, Mumbai, and Dr. Divendra Dakat from NIPER, Kolkata. So I request all of you please join on the dais for the valedictory session. Professor Evan. Professor Evan would. I request Dr. Radhakrishnanan, the Registrar NIPER Guwahati, to speak few words.
Good afternoon, everyone, and good afternoon to the dignitaries on the stage. So, thank you for giving this wonderful opportunity to host this ADDMC-23. So, I'm happy to see the successful completion of the MIT and DOP sponsored two-day workshop ADDMC-23. As mentioned by Director NIPER Guwahati, the Department of Medicinal Chemistry is making good progress since the inception in the year 2018. With the help of MIT, NSM and DOP, we have successfully established supercomputing GPU plus CPU infrastructure, paramembryo, with the artificial intelligence guided drug discovery and machine learning capabilities. It also serves the needs of all other departments within the NIPER Guwahati and outside. In the workshop, we are lucky to host eminent speakers who gave essential exposure to the participants online and offline. I'm sure the lectures and training sessions have empowered the youth and young minds with the right foundation to expand further. We welcome you in advance to join the next year's third session of the ADDMC 24. Thank you and all the very best.
Now I request Professor GPS Raghava from IIT Delhi to speak few words.
Good afternoon, everybody. So I want to say a few words about this institute because I am attached with this institute since the inception of this institute. When it was in the old building, I came many times. One thing I like about this institute is it's growing continuously. I think that's an exception after the NIPER Mohali that you have your own campus and it's very well built up. So though I visit first time your campus, excellent campus actually. And from beginning, you are organizing a number of workshops, conferences. That's very useful, not only for the NIPER students, but in Guwahati, but for the other institutes as well, actually. So here in 2 days, you have the excellent lectures. You have been exposed to the different people. So I will not take much time. Only scientifically, I want to give one message actually. Because nowadays, we are sometimes confused with the new terminologies. Like, for example, you heard day to day AI, artificial intelligence. So sometimes you feel I am biologist, I am pharmacist, blah, blah, blah. How can I do the AI techniques and all sort of things? But believe me, AI means artificial intelligence. What you have, real intelligence. Yes, that's fact. When I teach in my class, I always say that whatever the machine learning technique I'm teaching to you, support vector machine, hidden Markov model, neural network, all these things, they are inspired by the human being. These are nothing, it's a program. So if you want to develop the new techniques, new learning, you think about yourself actually. How you think, how you solve your problems actually. Then convert into the computers actually. So don't go into the terminology, like same like programming. Sometimes the student feel we cannot do the programming. It's nothing instructions. Let's say I am giving you instruction, you do this job. That's all. So these are these simple words. I'm not going into the science. I'm just telling that have the confidence in yourself. You can do it actually. Okay, that's all. Thank you.
Thank you, sir. Now I request all the dignitaries on the dais to distribute the certificates for the participants, especially who joined from out of the institute. I would like to call upon the first participants, Nivedita Ghosh. Can you please come on the dais, please? Nivedita Ghosh. Nasreen Ahmed. Nasreen Ahmed. Fasid Ali. Priyanka Bora. Yeah, Hemanta Kumar Gogai. Shabnam Nargis. Parthapratim Takuria, Arjiana Sultana, Arunab Arantara, Chinmay Maur, Chinmay, Pranami Changmai, Pranami Changmai, Jerifa Ahmad, Jerifa Ahmad, I think it's wrong. Pallavi Boyan, Pallavi Boyan, thank you, sir. Thank you. So all the internal participants can receive the certificates from the registration desk after the validity session. And there's a feedback form will be available to you by evening, and you can fill the feedback form and give us a feedback so that we can try to improve for the next academic session. And now I'd like to request Dr. Vaibhav Deshik for the vote of thanks.
Dr. Vaibhav, I just have a few words to say to the students.
Please, sir.
Yes, please.
Sorry for. Okay, so I want to ask some questions about at the end of all the sessions that we had. Let's be very honest. A lot went through these 2 days. Yes or no? A lot was taught to you. And let's be very honest. How much did you imbibe? How much did you learn? How much did you gather? Let's be very honest. Don't answer that. Okay? Now, don't be discouraged. Because many of the things that were spoken to you, you have been exposed to these things for the first time. For the first time. Like, for example, I presented Evans. Then Professor Kunal Roy presented Q Rasar. I saw that for the first time, and likewise, you also must have seen this for the first time. And it is very hard to grasp whatever is presented. There is so much of data. Okay. You know, students, don't be discouraged that how much did I take away from the thing? What I want you to understand, one thing to take away, all that we presented was done by our students. Right? So, what does it imply? One day, your professors will go to some other venue, maybe internationally, and present what you have done. Right? So that is the encouragement I want to give you. All that we have done, presented out here, okay, it's been years of work. It's a culmination of so many of our students having done these things together, and we presented in a nutshell. And it's very difficult to talk to you about 5 or 6 years. The work that I did must have spanned 7-8 years. To put all that 7-8 years into a 40-minute presentation so that you can understand, it's not easy. It's not easy. But all that I want you to say that, think of this, that someday, what work you'll be doing here, and maybe your juniors will take over. Maybe you are using your seniors' data and doing, someday your work is going to be presented by your professors out here, and you'll feel very, very happy. That's the take home. So don't be discouraged that I must have imbibed just 5 or 6% of all that was presented out there. Don't be discouraged with that. All that we want to tell you is that this is a body of work done by our students. you can do such wonderful work. There is great potential here. When I look at it and I see the experimentation facilities that you are going to have a 600 megahertz and a 400 megahertz NMR. How many institutions in this country have that facility? I heard that you're going to have an ITC, right?
Yes, sir.
How many institutions have that facility? Even think of the top institutions in this country. How many? How many have an ITC? Okay. And what else you're going to get?
Long list.
SEM.
Yeah, yes.
How many institutions will have an access to an SEM? Think of the potential that you have so much of resources, so much of facilities out here. You can do astounding work. You can do astounding work, and all will depend on you. You have resources, but finally what you will be able to accomplish is all dependent on your efforts. Work hard, you'll be able to publish great papers out there. Okay, so my best wishes to you, and maybe someday if you get the opportunity, maybe we'll see that, oh, your professor will tell us, you know, those students who were sitting at your conference some 2-3 years back, this is what the work that they have done, and we feel very happy. Okay, God bless you all.
Thank you, sir, for enlightening and enthusiastic post for all the students who attended here. Thank you very much for that kind words. So now over to Dr. Dikshit.
Wow. So yeah, let me just start with the first and foremost. I would like to thank our sponsors, the Ministry of Electronics and Information Technology, Department of Pharmaceuticals, and our software collaborators, OpenEye and Solis, for partly sponsoring this event. But our special thanks to our director, Professor Murthy sir, for his continuous support and guidance, without which this department and the event would not be possible. So all great thanks to him. We are also grateful to the registrar, their office dean, who are here with us, our in charge who had to leave due to some urgent work, and the advisory committee of the workshop. And also we received continuous support and guidance from them so that we could put all things in one place. And I should not forget our finance and account department and the purchase team, and also the continuous support of our CCC team. And please forgive me if I am missing something, but nonetheless, I must thank my colleagues in the Department of Medicinal Chemistry and the organizing committee, other faculty members, staff and students, especially who tirelessly worked. I could see them running here and there for the last 2 weeks to make this event successful. Overall, we had more than 500 participants online, and around equal number registered online, and around close to 100 registered for offline. But and I can see the seminar hall almost full. So there were many important messages for her. As Professor Coutinho said, this probably was the most important message that even excited me to, and I want to be a student once again, which I will continue to try to be. So, but nonetheless, Professor Jairam, who joined us on day one as a chief guest, he stressed on developing indigenous tools. Professor Bhartam again highlighted how to think in 3D, and Professor Sastry encouraged us to develop open source software. And Professor Evans in his talk mentioned not to forget the kinetics and focus on basics and understand the tools in depth was the message by Professor Kharkar. And we should keep our own virtual machines all the time ready. That's Professor Raghava gave a nice exposure to the Docker and cloud computing system. Read across and cure RAS RASA were introduced to us by Professor Roy. And Madhvi Sastry ma'am told us about the free energy and its importance in how water affects the protein interactions. And for Dr. Dhakad from our sister institute told us about the new ways of defining chemical identifiers. And Professor Dr. Ashish from Solis gave you exposure to the Discovery Studio, and Dr. Jaimin from Pfizer told us many new things about the dubs and other proteins today. So with this, we feel enriched by interacting with the experts and getting real hands-on training. We'll put the recorded session on YouTube very soon in the next 2 days. And you can also take advantage of the older YouTube channels from the last year's ADDMC. And as mentioned earlier, in-house participants can collect their certificates from the registration decks or latter. So don't worry, we are there for you. And finally, thank you all for registering, joining online, and special thanks to those who could make in person here from the nearby institutions. And with this, I would hand over it to Dr. Krishna, who will give you some final points about what is to follow the tea session. Thank you.
Yeah, thank you. Thank you, sir. I think that's what everyone is waiting for. Before dispersing to your places, please have your, can I call snacks or high tea? Yeah, maybe you can take the high tea and then you can go back to your places. Thank you very much for joining. Thank you.
Scientific expertise is shaping innovation and differentiation across multiple industries, including life sciences, consumer packaged goods, energy, process and utilities, industrial equipment, natural resources, high-tech, and aerospace and defense. In life sciences, Dassault Systèmes Biovia helps researchers to model individual processes within cells to identify the most promising candidates for drug research, development, and commercialization. In consumer packaged goods, Dassault Systèmes Biovia helps harness new biomaterials, smarter manufacturing processes, and innovative lifecycle assessment tools to reduce environmental impacts and move products to market faster. In energy, process, and utilities, Dassault Systèmes Biovia computational modeling and simulation tools reduce cost and increase profitability by optimizing plant engineering, construction, operation, and decommissioning. In industrial equipment, Dassault Systèmes Biovia helps manufacturers achieve disruptive innovation by optimizing the complex chemical transformations and processes that convert raw materials into functional devices, including batteries, displays, and wearable systems. In natural resources, scientists, engineers, and planners use Dassault Systèmes Biovia materials measurement, prediction, and analytics to more sustainably plan the commercial use of natural materials and Earth's resources. As the high-tech industry moves beyond Moore's law to functionally densified, highly integrated, complex designs, Dassault Systèmes Biovia is a critical enabler of polyfunctional materials design. In aerospace and defense, Dassault Systèmes Biovia modeling tools have advanced the development of strong, lightweight, and easy-to-manufacture carbon fiber composite materials for aircraft structural parts. With over 225 full-time PhD scientists on staff and an active science council, Dassault Systèmes Biovia continuously conducts innovative research across a broad spectrum of disciplines. Dassault Systèmes Biovia is committed to science. Over $1 trillion of scientific projects leverage Dassault Systèmes Biovia. Over 2,000 companies worldwide, delivering scientific solutions for more than 25 years. Scientific solutions created by scientists. 110 patents generated. 38 scientific awards. 1,200 peer-reviewed publications. 29% PhD. 38% of staff have more than 10 years in science industries or scientific projects. More than 20% of staff have held university positions. Dassault Systèmes Biovia advances chemistry, biology, and materials, helping scientists innovate, invent, and create. Dassault Systèmes Biovia, scientific solutions created by scientists for scientists.